Okay, good morning, everyone. I think that's everybody here. We'll have a little, helping on how to connect to the internet. So don't worry about it right now. For the first two lectures, we don't need internet, okay? And we'll have a break for the internet connectivity and so on. So for now, let's get seated. Good morning, everyone. I think that's everybody here. We'll have a little helping on how to connect to the internet. So don't worry about it right now. For the first two lectures, we don't need internet. Okay? And we'll have a break for the internet connectivity. Okay, so welcome to CompBio Bangladesh. It's a part of a initiative. It's called CompBio Asia. We are hosting similar workshop across. We hosted already two. This is the third one. We hosted the first one in Thailand, then Indonesia. This is the third one in Bangladesh. And I'll go a little bit over what's our goal through this workshop. Our, first is like our sponsor is Asia Connect, and then TEIN. They are supported by European Union, so they are our sponsor. And also the Protein Society of the USA is also helping us. And in Bangladesh, the teams that came together to host this workshop, to make this workshop happening, they're Dhaka University. They're the local PI for the grant that we got from TEIN. University Putra Malaysia, who are the major host of the grant. And then, of course, KUET and Khulna University being such a gracious host, hosting us. And then Kent State, some of our participants are joining from Kent State, and Kent State has facilitated that they can join, and also they arrange so that we can get computing resources from Ohio Supercomputing Center, and then I am from University of Montana. So those are, people from all over, from two different continents, they came together to make this happen. There's a lot of work but we are happy. Finally, we are here, so you are ready to start. So let's start. And okay, so again, a big hand to our sponsor. And so the idea behind arranging this workshop, computational biology, again, why the term computational biology? Because bioinformatics is a more better known term. The reason is the goal of the bioinformatics and computational biology is to help understand biology, right? And biology is such a vast field. It starts from atoms to all the way to organs and so on. So different aspects of biology, to be able to help computational of different aspects of biology, we have to have different kind of science or different kind of models. And I think as computational biology is that over-encompassing, that encompasses all the different kind of science or models we do to help understand biology. Bioinformatics is one part of it. Now, because it is such an interdisciplinary, it is very hard to get a good training in any of the universities. There are only few universities around the world where you can get a good training on different aspects of computational biology, because it's such an interdisciplinary field. It's incredibly interdisciplinary. And I hope at the end of the workshop, you understand That is how interdisciplinary it is, that in future workshops, there are more students can come from physics, math, engineering, not only from biotechnology, okay? So we need it to be a successful, vibrant community. You need input from everybody. I am from physics background. But interdisciplinary brings a additional challenge and anxiety. When a student start, they have the anxiety, they're like physics terms, chemistry terms, or even biology terms. Do I understand or not? And that's normal. That's for anybody, right? It's for even like when we start career, is the same thing. So, and there is a nice paper, this PLOS computational biology. They published this like 10 simple rules of different things. So this one was 10 simple rules for navigating computational aspect of an interdisciplinary PhD. So we can borrow the idea. So when you get into a research program, doesn't have to be a PhD, whatever level you are doing, and you are approaching an interdisciplinary field, how do you approach it? Okay, the first part is called get your ship together. That means like you start building, you start understanding the tools that you need. Like, it's like, okay, I need to pick up some programming. I need to pick up some math. Don't worry about the bigger picture here. Just start gathering those tools, okay? So after you gather that tool, so now once you gather, and we'll gather some of the tools here. After you gather those tools, now you know like, oh, what are the different tools can do? So then you set your course. Then you decide like, okay, now I know the pros and cons, the assumptions made into different tools. Now I can confidently set a goal for my research, okay? So if you do it otherwise, you're going to get screwed because you have to first understand what kind of tools you have in your hand before you set up a goal for your research project. And then after you set up your goal, at this moment, you're just setting up a goal. I'm going to cure diabetes. I'm going to cure cancer, whatever. Like you have to be realistic though. And then you start reading the literature. Okay. So after you set up your goal, you start reading the literature. And this will be overwhelming because these are all interdisciplinary, but you have to be just patient. I had to sit down 3 years after getting my PhD in physics. I had to sit down 3 years in biology courses. Very painful, but very rewarding after, sitting down 3 years during my postdocs. But that's what you have to do to excel in a multidisciplinary field. And then once you have read the accounts, what that will give you is like, for my field, these are the things that have already been done. So I understand what other people can do. Now I can start my research, okay? So after you set the course, read it, and then you start the research. And sometimes there is a lethargy, like to take a voyage in such an interdisciplinary field, like, this is overwhelming, but just go ahead and do it after you get some idea. And then once you start the research, that's when you're going to mature in the sense like you are going to like fine tune, like, okay, I'm going to exactly do this for my work. I'm going to exactly do this. You're going to set your course. And then the next part is very important, okay? Once you write a script for yourself, you do your work and you say, over is done. That's not true. Once a script you write, you're going to come back after 5 years or 10 years. So you may use that script. So if you are not organized from the very beginning, forget about it. Once you are in a professional career, you don't have time to come back, rewrite a script, rewrite all the documentation. You just don't have time. So just do it now. Okay. If you do not do that, just think about your script is lost. So this is the time. If you write a script for yourself, write documentation and organize it. It is very important because those scripts are the, earning, that's our bread and butter for computational biologists. You have so many scripts you'll put in your computer that you're going to use it later. Okay, so be very organized. Okay, and then, well, I mean, the later part is like, once you mature, and then, you should tell others and so on. But at least the initial part, my point is like, don't get overwhelmed. Just follow these simple steps. Learn the tools. After you learn the tools, what definitely you should learn are what are the assumptions behind the tools. And once you understand the assumption, then you set your research goal, like, okay, in this, my research, I can do this. And then read literature. And other point to be remembered is like, definitely store your scripts with good documentation. Okay, so in this workshop, we'll help you at least to achieve some of these. And how are you going to help you? So first, I'll encourage that you might be good at one aspect of computational biology. Try another aspect. You might be good at sequence science. Try modeling, try AMD, or the vice versa. Because as you try more aspects, you can answer bigger picture in biology, okay? So the first is like, in this workshop, we'd encourage you to venture into another branch. The lectures will be introductory, because the reason is, a lot of you might do not know one subject group, but do not know the other one. So that's why the lectures will be introductory. It's intentionally. It doesn't mean that we don't want you to learn more things, but it's intentionally introductory. The way that you are going to learn is first as hands-on, and the second is talking to us, talking to the instructor, okay? So if you understood the subject introductory, you want to have some deeper question, come talk to us. We have a separate room here. We arrange. If you have, some of you want to learn deeper on a subject, I or Sabrina, one of us will go there. We'll arrange a special lecture for it. That's the way you are going to learn. So first, understand the introductory. If you want to learn more, we'll arrange something, okay? And then the other part is, I want all of you to help each other, because that's the way you are going to learn. I cannot, or our instructors, they cannot go and teach you everything. You have to learn, and you have to learn from each other. And once you make this peer-to-peer connection, you are going to carry it for years. These professional connections are so helpful. So that's the other part that I want you to take from this workshop. And then, hopefully, whatever work you are doing, after when you get back from the workshop, you can bring new dimension to your research work from the new things that you learned, or the HPC resources that we are providing, okay? So that's like the overall goal of the workshop. Now, let me introduce you to, Protein Society, who was one of our sponsors. They have annual symposium. Typically, they held it in USA, but it's a really good. I try to go there every year. So when you become more, later in your career, if you have the chance, please visit one of the Protein Society annual symposium. It's a nice combination of work, computational or experimental, anything related to protein. Okay, so, and then our website is combioasia.org. That's where we update all the CompBio Asia related things. And one of them is, of course, CompBio Bangladesh. And then we have a YouTube channel, CompBio Asia, and which is currently being live. I never gave a live presentation before, so it's a challenge for me too. Okay, so our instructors, that's me. Sabrina is sitting right there. And then we have 3 of our previous graduate. Sajjad is somewhere here. Sajjad is right there. And then Shishir and Rahat are right here. So 5 of us are going to help you to navigate to the next 5 days. Okay, so typically 1 day for each of us, and then we had, behind the scene, a lot of people work. Khademul and Shubro, Khademul is from Dhaka University, Shubro is from Bosch Institute, Kolkata. They couldn't make for one or another reason. Vish is from Norway. He will have special topics. So every day, 9 p.m. to at least 10 p.m., if not 11, there will be special topics. And Vish will provide that as a Zoom link. It's not compulsory. If you have the energy before go to bed, just join that. And then, any question and answer, especially for the for our participants who are joining from USA, one of us will be there to answer your questions, any kind of questions that you may have from the previous days, hands-on. So Vish is from Norway. He is helping us from Norway. And then from Kent State University, Professor Javed Khan. For all of for you who do not know Professor Javed Khan was the BD RAN. All the connectivity was his brainchild. He because of BD RAN, we can have this kind of workshop, which provides us the stable and fast network, and people from all over the world can join, and we can connect to HPC, do our scientific work. It's one of his brainchild. Philip is Dr. Khan's student, and Jane is from the KSU Computer Science. She is organizing the workshop on that part. So there is another group of people joining from Kent State University. And then some of you already have met Wilbur from Ohio State. Dr. Oma is from Ohio Supercomputing Center. And Dr. Hee-Chang Na, you may not have met him, but he has helped us installing all the software at the supercomputer. And this is our genies of Aladdin, Aladdin's genie. Okay, without them, this workshop wouldn't have been possible. Okay, so what we're looking at is like assistant registrar Dolan Babu, and then Pradeep is right here, system analyst, and I do not see Mr. Tariqul Islami, but you'll see him. He's this jolly guy running around, really nice. He's a faculty here. Shubroto, you probably have met him. He's bringing you up and down here. And then Mihirlal is, right there. Okay, another system analyst. So really, without their help, this would not have been possible. It's already a headache to arrange a workshop. It's 10-time headache when you try to do from USA, okay, when you try to do from far, okay? It's only possible because I can rely on these guys, and this. I said, like, we need a great room. You have the better room than I could have imagined. We need a good connectivity. You have better connectivity than I could imagine. So yes, thank you, all of you, for this. And special thanks. This workshop was supposed to be somewhere near Dhaka. And, the Khadimul had to leave, and we didn't have enough manpower to Dhaka. It's when Professor Alamgir was visiting me, I told him, like, I'm feeling a little nervous about this workshop. He said, like, come to KUET, we'll make it happen. So it was Professor Alamgir, who was a vice chancellor here before, now is a member of UGC. It was because of his helping hand that we are here today. And then the vice chancellor of here, he also, gave us a really warm welcome. I hope he can join us today for dinner. Bimo, he is the PI for the grant that you got, Asia Connect. You haven't seen him. He wanted to come here, but this is middle of the work, his semester, so he couldn't come here. But behind the work, a lot of the budgeting and stuff, and Bimo has done. And Tasmima Hussain, if you know Anonna magazine, she's the editor of the Anonna magazine in Bangladesh. Any grant that comes is usually reimbursement based, in the sense that whatever money we spend, we have to spend out of our pocket, and then we get reimbursement. And it's good for countries abroad where the university has big fund. You can pull money and then get reimbursed, but it's very difficult to do it in countries in Asia. Most of the universities do not have big fund. So we needed the money to spend upfront, and then say, like, and that's what Tasmima auntie came and said, like, okay, we'll give you all the money and then get me back. So it's a really, she's just behind. She didn't even want me to mention her name, but that made it happen. And then BD RAN, they worked with us, and they are going to, BD RAN and Ohio Supercomputing Computer. You don't get to see it, but next 7 days, they'll be on alert so that there is no disruption of network from here to Ohio. Okay. So it's all on the, because you all will be working on the HPC. And then the Khulna University, along with KUET, is being your host. If you haven't got the program yet, we are going to start 8:30. So from tomorrow, please be here at 8:30 because there will be people waiting at the Zoom session on the other end of the world. So please be here. Typically, we'll have 2 lectures in the morning, and then mostly hands-on. On some afternoon, there might be another lecture, but we'll focus mostly on the hands-on. And then the first 3 days, we'll be working on the HPC. And then the third day afternoon will be transferred to a board. So the subsequent lectures on the board will be just simple lecture without HPC connection or one-to-one interaction and so on. And so for the first 3 days, it will be on HPC. We'll be working on HPC. Okay. And then, okay, let's get started. Let's see. We are 17 minutes late. That's not too bad. Okay. Okay, so first lecture will be by me too. Okay, so let's go to. Okay, so in an ideal world, we would have started with the genomics first lecture because you learn about the sequence. Then we would have started the modeling, so you learn about the structure, and then we would have moved to dynamics. Okay, but we had to bring the dynamics lecture in the beginning because that takes the most of the time, so that once you start some dynamics, molecular dynamics simulation, so that you can get to see the result. So just whatever you learn, put it on the third day. Okay, so then it will make sense, because you should start at the genomics and then modeling, and then you should move to molecular dynamics. But for logistical reason, we only have 3 days here, so we're going to start with here. And then Shubhra was supposed to give a lecture, and then because of health issue, he couldn't make it. So I am borrowing the lecture from Charlie, who was who gave this lecture in Thailand. So I will be just going through that lecture, and then if you have any question, please stop me, because this is supposed to be an introductory and interactive. You can ask the question in Bangla or English, doesn't matter, I understand both. And we'll try to help you answer as best as we can, okay? So first question, molecular dynamics. If you haven't heard the term, by the end of the lecture, you'll understand why, what it means. But the first question is like, why do we do it? Okay. So, if you look into an atom, there is actually nice, I should have got the video. It's called Power of 10. The Power of 10, this video came out in 90s or something, where you can, is an animation of you zoom down by a factor of 10, what do you see? And as you can zoom down and zoom down and zoom down, finally you'll come to see an atom. An atom is always jiggling and wiggling because of the temperature. The only time an atom is frozen if you go to T equals to 0, like minus 273 Kelvin, right? So in the biology in your cell, every time an atom is always fluctuating, you always have some kind of kinetic energy, okay? And that kinetic energy makes us actually living, like, how well tuned those kinetic energy in a biological system. So to understand something at an atomic level, we have to somehow account for how the different atoms are fluctuating. And the way you calculate that is the field called molecular dynamics. There are other ways you can calculate, but the most popular and most efficient one up to now is the molecular dynamics. So, so the answer is like, if you want to replicate the thermodynamical effect of small molecules, how they're fluctuating inside our cell, we have to do some kind of molecular dynamics. And the molecular dynamics, this is, it has been called a computational microscope, okay? So in computational biology, you'll see certain terms as name called omics, like bioinformatics, whatever omics you can think. And then there are like other part of computational biology, molecular dynamics is one of them. There's a fundamental difference between them. Omics is you already have the data and you are going to find a pattern in the data. And then the data are coming from experimental observations. So that's omics. And molecular dynamics falls on the other part. It generates data, but the experiments cannot. Like it fills out the gap where we do not have an experimental technology to generate those data. So it fills out the gap in a microscopy. So if you go in a microscopy, you have you have a light microscopy, and then if you go further, you have X-ray. Then if you go further, you have electron microscope. But if you want to go even further, then you do not have any experimental tools to look into a live molecule jiggling and wiggling. And that's where the molecular dynamics comes in. That's why it's called a computational microscopy. So there is a fundamental difference. Here you are generating data as if you are doing an experiment. In an omics, you already have the data. Then you are looking for a pattern in there. Okay. So, so again, these are models that tries to generate the data. So how do we do it? We have to be very faithful to the physical laws so that we can generate a physically relevant data. A good review. This is actually is a nice review, a molecular dynamics simulation for all. It didn't come out too long back, 2018. So it has most of the updated stuff, and it's very well written. So, when you get time, read it. I'm not sure if I put this paper on the Slack. If I haven't, I'll put this paper up. And to all of you, please follow the Slack channel. Please communicate via Slack channel and so on. That's how we are going to communicate now and communicate after the workshop. So be active on the Slack channel. Now, why people do MD? Okay, let's see. Well, if you're doing, and this is so true, as a lot of people come to me and say, like, I know if I do this MD, I'm going to find the drug for this cancer, because you're hoping like something amazing will happen out of the MD simulation. Okay, and this is so common. I hear it so many times. And if you want to say like my protein aggregates, I want to see how my protein aggregates. And, a lot of things that if you, like there are a lot of things like you know experimentally like something will happen, and you come to try to design an MD simulation. But these are not hard to, these are not easy to design. So if you want to see something amazing, that's one reason. The other reason, most of the time you'll be doing for this, okay? Because this is the more reliable part that you can do. So, which is like you predict your thermodynamical quantities, okay? Because MD is easy to replicate the thermodynamics to an MD simulation, like binding affinities. So that's like, you feel like, nothing amazing has happened, but that's actually more reliable, robust way to do. You can do stuff on the left. That's a lot of work. There's a lot of knowledge of statistical mechanics is required, and you have to be careful. But people do it for both. It's just I'm putting the expectation. Most of the time, you'll probably do stuff on the right, on the left. Yeah. So when you do an MD simulation, and we'll do it today, what you are expected to see is you are expected to see a molecule in motion. It's like a movie, where you have snapshots of the molecules at different pace. And if you put them together, it will be like a movie. It's really a movie. Okay. However, what that movie corresponds to is, if we do everything right, how that molecule behaves in a solution in a real life. Okay. So that's what we are trying to do. And you can connect those to thermodynamics. We are not going to go into details of thermodynamics, but if one of you, if you have to discuss about it, I can discuss. But the hope is, there is an ergodicity theorem which says, like, if you watch a molecule, a single molecule long enough, for infinite time, then if I have an Avogadro numbers of molecule in my solution, then I can find the behavior of thermodynamical behavior of those Avogadro numbers of molecule by just watching one molecule long enough. So that's the philosophy behind it, that we are going to watch a single molecule long enough so that we can replicate the thermodynamics behavior in the simulation, in the water, in real life. So motivation is, if you want to see something happening, but if you are trying to ask the question, I just want to run the MD to see something happen, that's not a motivation. That's not going to work. So you just think about MD as an experimental tool. Just because it's cheap doesn't mean that you're just going to do it. Okay, if your lab had the constraint on the money, and you say like, I want to study how the genetic variations in Bangladesh among different people, something like that, you're just not going to start picking up people from the road and have a genetic sample, right? You have to have a experimental thought and setup, and then you start, because sequencing costs money. So you have to think same way. You're just not going to start an MD simulation because you have the computer and think like, let's see what happens. Nothing will happen. You have to have a careful experimental plan to see like, how can I make an experimental plan so that I can see something happens in the MD simulation? Okay, so how it works. So in MD simulation, what we calculate is the force between two atoms. And then here, the atoms are very stylized in the sense the atoms are we made a lot of approximation what an atom really is. But let's say if atom looks like a simple sphere, okay, for now, atom doesn't look like that, but let's assume. So if an atom looks like a simple sphere, if we do not have any other force on it, then Newton's second law, if it has some velocity, is going to just keep moving on, right? Until another atom comes in. And another atom comes in, so it can have multiple different ways. It can collide, or most of the time it will have an attraction, it will bend its path and so on. Okay. So that is the thing that what we do in MD. We do a time series of how different atoms are interacting with each other, how different atoms are having force, providing force to each other, okay? So we start with the initial setup of atoms, and we see, and we provide them some kind of velocities, and then let's see how they insert force on each other over the time, and we look at that time series. So that's the data that they're going to come out. You're going to see how different atoms are behaving in the presence of each other. So yeah, we start with a set of initial positions. We give them an initial velocity. We calculate the force, then move the atoms according to the force. Then we go back to the step again and repeat it. And typically, each steps are calculated as of the order of 1 to 2 femtoseconds, but there can be a larger time step. Like we calculate first what will happen at 0th time, then what will happen at the 2 femtosecond time, and what will happen at the 4 femtosecond time, and so on. But there are techniques to do it larger, but typically it is done at 1 to 2 femtoseconds. The reason is that's the vibration frequency of hydrogen. So you want to capture everything. So hydrogen is the fastest thing that's moving, is the lightest. So you want, that's the time step that we choose there. But there are other ways to go around it. Okay, so we have the initial velocity, and we say like we update as the force go on. But how do we update? So if ideally you should calculate the force, but if you are not from physics background, force is a very messy thing to calculate because it's a vector. Vector always has 3 dimensions, and you have to calculate the angles, and you have to calculate the so on. So instead, what we do, we calculate potential. Potential means like it's a scalar. It just, you don't have to understand all of it. The bottom line is like, it's easier for bookkeeping purpose to calculate potential. And then force can be easily calculated from potential by taking a derivative. So even though our goal is to calculate the forces, but for bookkeeping purpose, we'll be using a potential. So from now on, all the terms that you'll hear the term potential, okay? The whole idea is like we want to calculate the force, but it's easy to do it through the potential. So an example is like, if I have two atoms, carbon and oxygen, if I connect it by a spring, if I measure the force, if you have a spring, the farther you go, the force is bigger. If you have in the what you call equilibrium position, no force, and then if you come closer, the force is again bigger. So that's what the force is like. It's a negative force because whichever direction you want to go, is want to pull you back the other direction. That's the spring. And then how far you go from the equilibrium. So, but it's easier to. Okay, so that's the force. Basically, it says the negative term means like it will be, wherever you want to go, it will pull you back. That's what it says. But it's easier to calculate this term and carry this term. And whenever I need to calculate the force, I just take a derivative. So that's why we carry the potential. So now in molecular dynamics, you don't have to understand all the math, but and a Nobel Prize was given for this. Okay, so that's not easy to come to the understanding for it. So, but let's understand what's happening, right? As I said, like I want to replace a experimental observation to molecular dynamics calculation, right? So I have to be as much accurate as possible. The most accurate way to calculate is quantum mechanics. But using quantum mechanics, you can calculate, there is a size limitation, how many atoms you can put in a quantum mechanical calculation, and also how much time it takes. Is typically you can do 1,000 atoms. It takes, weeks to calculate the forces between 1,000 atoms and so on. So we don't do quantum mechanics. So we have to do some kind of approximation where the quantum mechanical force can be approximated by our Newton force, like springs and bonds, like, connected by a spring and so on. And these are the terms that you see it on the right, okay? So the term that, and these, even if you don't understand all the physics, but just remember the first term is like if two atoms are connected by a bond means like an electron is being shared between them. So if the two atoms are connected by a bond, then they cannot go too far, like they will be stuck. Depending on single bond and double bond, they're very stuck to each other. And we can approximate that by putting a spring with the proper strength. Again, this kind of potential, wherever you see kr squared, that's a spring potential. That's like a spring. Okay. Angles, similarly, is in a sense like in your protein molecule or in biomolecules, the angle between two atoms, they can, there are certain preferable angles. And again, you can have that at a spring, like put like imagine like if you have like two atoms, like three atoms, and you can put a spring between them, then these two atoms angle will be like, can vibrate around that mean value. So that's like a spring in the angle direction. This is a little bit complicated. It's called dihedral when you have four atoms, then how the four atoms can rearrange. And then you have electrostatics. This is electrostatics. And then you have something called van der Waal interaction. What it does is it makes sure two atoms do not sit on top of each other. So those are the 5 kinds of major forces that you are going to see. But there is a lot of physics goes on determining these values of kr, k theta. That means like what will be the strength of the spring and what is the optimal value where there will be no force. There's a lot of physics go behind that, and we'll have a lecture later today. So the idea, running a molecular dynamics simulation is very easy. You put your computer, the computer spits out. But to develop that, to come to that point, a lot of work goes how we can transfer a quantum mechanical force calculation to this simple Newtonian mechanics force calculation, and how we can derive these constants. And that's where all the physics goes. Okay. So, so we'll not be developing any force field. That's called a force field, like where you derive all these constant, but we'll get a peek into the force field so that we know what goes into when you run into an MD simulation. So how it works. So, as I said, we start with the position, we start with the velocity, and we iteratively calculate how each other puts force on each other, and we see how a molecule evolves. And then from those things, we can predict different properties of the system. Okay. But again, as I said, just remember, before you can start, there are so many values of the constant that we need to be derived, and it has been done by other scientists for us. So we are going to borrow from their work, and we will use them. There is currently, okay, so this part maybe I should reiterate very well. Currently, because of the requirement of the computational resources and the power that we have, typically you can run a system for a microsecond. That will be a typical, and that's like if you have access to supercomputer for like 3 months, 4 months, and so on. So typically a microsecond. The richest people, they can run in milliseconds. There are some companies in USA, they can run in milliseconds. But a biology can happen in seconds and hours. Like when you're seeing a biology, that means like if the two molecules come, do they interact or not? And they can interact over the time period of seconds or minutes or so on. Okay, some can interact at the time second of microsecond, but there are not many. So remember that time scale. If you are going to run an MD simulation, you're going to say like, I want to see these two molecules are going to dissociate. You might be disappointed because after 3 months, 4 months, you are running 1 microsecond, but your biology happens in a second or in a minute. Okay, so that's not a proper question to ask the MD simulation, to design an MD simulation experiment. Okay, so you have to be, so if you want to just see the brute force way to see the biology by MD simulation, currently we do not have this capacity. How do we do it? That will be our next lecture, where what we do is like, as I said, somebody has already developed the parameters for us. We're going to take those parameters, okay, and those parameters, when somebody has developed us and put this in a nice library or format, that's called a force field. There are a few different kind of force field. We are going to use those force fields, and then somebody else has made a software that will take the force field, that will take your protein and calculate the steps and calculate how the molecule evolves. That's got an MD engine, like molecular dynamics engine. So there will be 2 parts. So a molecular dynamics engine, all it does is like, you have to give it a initial position and velocity of a molecule, and you have to give it a force field, and it's just going to calculate the forces one after another, and so on. That's the molecular dynamics engine. That's all it does. You have to provide the force field and the molecule. And the force field, what it does is like it develops, in a force field package, it develops all the constants that you have to develop through all this physics. So we will run an MD engine, and we'll see some of the parameters in the force field. Some of the popular MD engines are Amber, Gromax, Charm, and if it is not confusing enough, it's also, they have their own force fields. So some force fields are also named Charm, Gromax, and Amber, and so on. Okay, so it's a little confusing. So, so that these 3 has their MD engine as well as force field. And then, but there are other MD engines who, they're just MD engines. They use the force field developed by others, like NAMD. I think we probably will have NAMD. We will work with NAMD during this week. Well, I'm going to skip that in the sense like I told that before, you have to have a good design of computational experiment before you start your MD. Otherwise, you're not going to get result. And a good design typically starts with having a structure, either an experimental, or we'll learn in our modeling part, you can calculate a structure from AlphaFold. And then once you start with a structure, like in case of a experimental structure, sometimes you'll have missing atoms. So we add the missing atoms. And then we add solvents, because everything in our cell, there are solvents there. Those are the typical steps. And then we find parameters from the force field library. Like, okay, I have my atoms. What are the parameters? And then we put it into an MD engine and we run MD. And I think that's in our next lecture. And then finally, they analyze the data. So again, running an MD is the easiest because there are 200 scientists around the world. They have developed the force field for us. There are another 200 scientists around the world. They have developed an MD engine for us. All we have to do is like click, it's going to run. That's the easiest part. The hardest part is to analyze it. Because if you do not understand what you are doing, you cannot understand. You will just have, and there are so many papers comes to me for review who just ran MD and say like, I saw these, I saw that. And I reject all of them. Surprisingly, half of them still get published. I do not know how. But you know, but really, if you do not design an MD experiment, well, you are not going to get anything out of it. So because remember, like an MD just can give you at most a microsecond worth of data. Your biology happens in seconds, minutes, and hours. So there is no way you can run and see MD simulation. So I get to see the biology. There is no way you can do that. So you have to design your experiment so that you can get the best information out of MD simulation. And that's where the analysis part comes. So, yeah, I already said that the actual part, running the MD is the easiest part. It's like analyzing the data and correlating with the experiment. That's where your understanding of science will come. So our take-home message is like the simulation can give us, insight between the physics and chemistry that goes to the atomistic level versus the biology of Avogadro numbers of molecules that we see in an experiment. So it's going to connect those two. And then, like when I started my postdoc, I was happy to run a simulation. Like I first published my paper in PNAS. I had 20 nanoseconds of data. That's like 5 copies, so altogether 100 nanoseconds. I was like, I have 100 nanoseconds of data. Nowadays, people throw away 100 nanoseconds of data because they can run like a 1 microsecond. So as the computers are getting faster, our accuracy is getting more. The people, we can do more. Okay, so it's an exciting time there, But yeah. Okay, I think that's end, and let's see how we're doing at time. 9:15, not bad. Our next lectures will start at 9:30. So the next 15 minutes, I'll take question and answer, as well as if anyone needs help with setting up the IP, so you can get help. So any questions? And if there's any question from online, let me know too. Let me see the chat. Okay. If there is no question, I'll understand everybody you understood, and we'll have a quiz later after lunch, okay? Okay. Yeah. How should we choose the Okay, so the question is, how should we choose the force field? For protein molecule, because protein has only 20 different amino acids, so it's already been developed. So now, even though the philosophy of the 3 different kind of force field that you see, CHARM, AMBER, GROMACS, the philosophy is different, but the end result is very similar. The philosophy is different means like in charm, the force field is derived if you, how do you put a water near an atom? Where do you put? So that you can reproduce the observable quantity like viscosity and solubility and so on. So even though the different philosophies are different, they all try to reproduce the same experimental values. So it actually doesn't matter which one you choose. Just choose one and just don't switch. If you start with one, keep with that force field. Just don't switch. If you switch, then it will be a problem. It can be a problem. And for small molecules, that's harder because small molecule, there are so many different varieties. So a lot of the time, you might be lucky to get already calculated force field. If not, you can probably get a quick calculation. If you cannot do through a quick calculation, then generating a force field for a new kind of molecule is very time consuming. In that case, you have to work hard to calculate those force field parameters. Yeah. Okay, any other question? Yes.
You said that we are considering protein in a solvent. What about the protein in lipid membrane complex?
Oh yeah, we do that too. Sorry, I didn't mention that. So yes, protein in presence of other molecules. So either water, ions, or lipid molecules. Yeah. So you can do that too. Yeah.
Setting the lipid bilayer membrane on protein recipient.
Uh-huh.
So where we get this information from? Like these atoms are considering in lipid bilayer.
So we will have the next lecture will help you. There is a group, they call themselves Charm GUI. So Charm, the original MD simulation, the father of Charm, Martin Karpras, got Nobel Prize for this idea. So a lot of current MD simulation people came from that lab. So they're carrying the Charm legacy. So one of the people, Winpil Im, he started called Charm GUI, like graphical user interface. He has developed a lot of methods where all these questions, you can go through his website and he'll answer it for you and we build it for you, so that because these are technical questions that once somebody has found the solution, others should not be bothered about it. And we'll have a next hands-on with Charm GUI, and the Charm GUI you can see easily, you can set up a system in membrane and so on. Yeah. Okay, if there is no other question, I will, who is going to provide the next one? You or you? Okay. So we still have 10 minutes. We'll take time to set up for the next one. And the next one will be on semi-hands-on. What will it be? Hands-on or semi-hands?
Actually, I think giving a brief on my hands-on so that they can follow the hands-on. So it will be a brief 10 minutes lecture on how to use Charm GUI and submit those files in OSC. And that's it. And they will, after that, they will just do their work.
So, okay, so you will have to follow, after a little bit, you have to follow with Rahat. So all of you has to be on your computer right now and be ready. I think you may have to transfer, like, how is it going to? Oh, you share your screen. Okay. Zoom session.
screen share দিয়ে দিচ্ছি। আশা করা যায় ঠিক আছে। Okay, ঠিক আছে। Okay. না এখন okay. Okay, can everyone hear me? Okay, I guess everyone can hear me. So thanks. For today's hands-on session, we'll be working with Charm GUI. All I am going to say for this session is actually included in the lecture which I have given yesterday. So I wouldn't worry about how to run for now. But what I want all of you to do is that follow what I'm doing now and later try those steps for yourself. Okay, so let's get started. So what is Charm GUI? Yes. So what is Charm GUI? Charm GUI is web interface which is developed by Charm Group, I guess. And it was actually a collection of bunch of tools which is actually developed for PDB or protein data manipulation, protein solution builder, or make a simulation or something like that. There's a lot of function in it. So you can go to the Charm GUI website and surf to the website. I'll be working with input generator from Charm GUI today. And specifically, I will work on PDB reader and solution builder. There is a lots of function in it. You can go through with those things if you like later. And you can ask me a question if you have later. Okay.
So if you just requested for an account, you have to wait for it.
Oh. Yeah, if you sign up for a day for now, you'll get notification for a day or two. Okay, so first you have to go to the Charm GUI website, and that is charm-gui.org, and then you will go to the input generator option. Okay, so in input generator option, you will have a lots of option actually, like PDB reader, force field converter, glycan reader. On the left side of left tab actually, you will have to select PDB reader and manipulator, and you'll see option to download or upload your PDB file. So okay. So in the PDB reader, you can actually put your PDB number if you know from the RCSB database, or maybe you can, if you have your PDB data, you can browse it through this option.
How many of you know about PDB? Everybody knows about PDB?
Everybody knows about.
Okay.
Great.
So yeah, so the first option, in the first one, you can either pull something from PDB or you can upload a PDB from your.
Yeah. So let's check. I'm giving a PDB number of ubiquitin. If you know about it, it's a simple protein of 2 chains. We'll see that later. Okay, and then go next.
Yeah.
Oh,
Okay. Hold on.
question.
Yeah. Yeah. So Raj, just
Yeah. So
take your time. Take your time. So that what is it?
yeah, you can go to the RCSB database, and if you want.
Okay. So let's take it slow. So if you have your favorite protein, if you know the code, just put that code. If you do not know the code, go to rcsb.org. That's the PDB. There are 3 different PDB sites. rcsb.org is one. Find your favorite protein from there. And once you are in that RCSB, whatever you search on the top, it will come and you'll get a 4-letter code here. Okay. So you can take that 4-letter code of your favorite protein and put it in the charm GUI. Okay. So 3 ways, right? If you have your favorite protein code, put it there. If you do not know, go to RCSB, find and put it there. Or if you have a PDB in your laptop, upload it. Okay. So let's give them a few minutes. When we'll wait for 2 minutes, when everybody is done uploading or getting, then we'll go to the next step.
Okay. For starter, you can search it in the RCSB database. Let's say lysozyme. One GWT. So you can copy the RCSB number from here, or maybe you can download it and then upload it in charm GUI. Anyone is fine.
Let's go to the charm GUI website. Yeah, the bottom. Yeah, so if you just give the number, the charm GUI is going to fetch it from the RCSB. Just give the ID, that's enough. But if you have some PDB file on your laptop, then you'll have to upload it. Okay, so if you just give the ID, it will fetch it.
So everyone done downloading the files?
So if you haven't done this, just raise your hand, we'll wait for you. You haven't done it yet. You did. So if you haven't done it, raise your hand. Okay, we'll wait for you.
Okay.
Okay, so while we are waiting in PDB, you'll typically see structures either solved by crystallography or by NMR. Those are the two types of structures you'll typically see in PDB. And then sometime maybe a model from cryo-EM electron microscope. But sometime you won't find the structures there because they haven't been experimentally solved. But with the invention of AlphaFold, we can solve most of the single domain proteins very accurately. So for a lot of protein, you'll have to download the structure from an AlphaFold database or another database to your laptop, and then you have to upload. Okay. So PDB is mostly experimentally solved structure. I think Rahat is showing us the structure of one of the proteins.
Yeah, I'm showing structure of ubiquitin.
And by just, okay, can you anyone tell how this structure was solved? Like, what is the experimental method? Okay, we have two different kinds. So X-ray crystallography or NMR. So why X-ray crystallography? You moved it away. Okay, why X-ray crystallography? Why? Okay, what is the clue here that's telling you it's an X-ray crystallography? Okay, what is the clue here that's telling you an NMR? Huh? Oh, because no, it looks like that's a representation, but it has been solved by an NMR, and I'll tell you why. Why is the clue? In X-ray crystallography, you solve a structure. You get a single model. I mean, you may have the side chains vary slightly differently because what you are calculating the density of the different atoms. So you get a density stress, so you can put your molecule there. In NMR, you get distance constant, which means like NMR experiment tells you whether two atoms are close to each other or not. They don't tell the structure. It just says like atom number 1 is close to atom 50, atom number 2 is close to atom 30, and such that. So once you get those, then you try to build a model that satisfies those distance constants. So an NMR structure typically will have 10, 12 different models. And you can see there are like so many models are overlaid with each other because all of those models satisfies each one of them is a single model. All of those models satisfy the distance constraints. So that's the clue that this is an NMR structure. An X-ray structure would have a single. Okay, so Rabia, are you good? Not good. Oh, okay. Let's see what's that. Okay. So let's go to the next step. Okay, so let's upload. Once you have uploaded.
Okay, so the file I downloaded right now, I'll just upload it. Where is it? You'll just have to upload and then click next.
Yeah, either upload or put the number.
Yeah, upload or put the number. Okay. As you can see, a lot of information about the protein here. You see that it's the experimental method of this protein is NMR, and the PDB ID, and what's the PDB about? It's about human ubiquitin and some information like that. Also, it provides that how many chains it have in its structure. You can see that.
Okay, so let's go to, you see that there's a select model. If you can click on the select model, right, the arrow, down arrow button, the select.
Oh, okay.
So you see like 14, 15 models. Those are the 14, 15 models from the NMR, that because all of them satisfy the constraints, right? And you can choose to work with any of those models. Okay, and if you looked at the picture, they're all very similar, right? So it's equally good if you work with the first model, if you do it as a default. But if you, for some reason, you want to work with another model, you can choose the model there. Okay, so then Rab, you're saying there are two chains in that.
Yeah, so you can manipulate your chains if you like. I mean, I can choose chain A or chain B if I like to work on that, and just unselect another.
Okay, so I have a question. What is a chain in protein? Anybody, what is a chain in a protein? When Rahat is saying it's a chain, what is a chain? Okay, so if I have two chains in that one, what does it tell? What does that, huh? Okay, so that means, yeah, that means like they are not connected by a bond. Yes, so there are two separate ones. So,
yeah, so as you can see, they're not connected actually. There are two bonds here. Maybe you can see more clearly. Yeah, as they are colored in different, yeah. So there are two chains here. You can select any one or both if according to your needs actually.
so Charm GUI does it for you. It actually finds how many chain it has in the in your whatever file you are working with, and it will give you the option whether you want to work with both or one of them. And also it identifies the residue number of the first and the last and so on. So you can see the first and last are given. And so it takes a lot of the work that you have to do manually.
Yeah. If I don't have this Charm GUI application, then I have to do it in terminal, or I have to edit that PDB text file. Okay. So click next. If you
okay, what happened to the next? Okay, so when you click next, another window popped up.
Yeah,
what it means is that window is actually a charm script. Now this is confusing.
okay, let me show that again.
Yeah, a charm means like a charm can be a force field, a charm can be a GUI, and a charm can be an MD engine, right? So it's really confusing. So that is a charm script, that means a charm MD engine script that popped up and was running in the supercomputer that's connected, the charm GUI is connected to. So this charm GUI is running that script, like I'm going to choose only one chain, I'm going to choose all those things, is running that script behind on the, I think this one is Lehigh University, it's running on the Lehigh University computer. But if you didn't have the access to it, you'd have to run it on your computer and do that manually. So when it clicks next, you'll see every time you'll do from now on, you'll see a script pops up. And that means like that script is running in Lehigh University computer. Okay. Yeah, I think like if you notice whenever you click next, you'll see a, there it is. That's the charm process has been evoked. So that means like a script is running on the background. Yes. Yeah.
Yeah, you can.
He's just showing demonstration that if you can play with both the chain or you can play with one of the chain. Yeah. Okay, why do you do it? Okay, sometime in an X-ray crystallography, because of what is it called crystal symmetry, that means like crystal packing, in the sense like in X-ray, the atoms are packed against each other, right? Because it has to be an array of molecules. And the part that you are taking the image of, it can contains two copies of that thing. So, and for your biological system, you may need only one copy. You don't need two copies. So then you uncheck one. Sometimes the two copies might be biologically relevant. There might be two different molecules interacting. In that case, you need both if you're working with both. So that's your call, whether you want to work with a single or two. Yeah.
Okay, in the next step, you can do a lot more manipulation, like you can add mutation if you like.
Okay, so let's go through slowly. Okay. So because there's a lot of here. Yeah. So let's go, like, let's put it there, right there. So why does an amino acid forms? Like this is a chemistry and I don't know the answer, right? I'm still going to ask the question. So when two amides come, right? And then you have an end of the amides are usually charged. Okay, and you have a water molecule that's coming and and it releases. Oh, see, I cannot answer question. But the bottom line, chemistry, but the bottom line is you have charge at the end, right? But in biology, the last and the first cannot be charged, amino acid sequence, because if they are charged, then they'll keep doing the interaction, right? So you have to have some kind of things at the bottom, the first and the last, that calls terminal residues or terminal atoms, so that it makes them neutral. So the first option that you see there, the terminal group patching, okay? And you have the option, if you see the first one, let's click on the first one, Rahat. Okay, so you see, I think the first residue of this molecule is glycine, okay? So that's why one of the patch that will go in the first is called GlyP. And what basically it means is a slightly modified version of glycine so that it has a neutral charge, okay? Or an acetyl, S means like acetyl group or something, that's more biological one, that typically you have an acetyl group in the front. So you can decide that which one to put. And sometimes you can think like, you know what, I want the charge to be there for my simulation. Then you choose none option. Because if you put none option, that means like whatever the hanging charge in the end of the amino, it will be there. Okay, let's go to the last portion. Similarly, yeah, let's choose GlyP here. Similarly, for last, you have a C terminal end, which may have some charge, I forgot, or a neutral, or you have different options. So all these are options so that your end is not hanging in with a charge. It has some biologically relevant molecules that change the charge. So that is the first thing when you open an MD simulation. That is the first thing you're going to do. You're going to decide whether I want the two ends to be. Okay. So whether we want the two ends to be have charge or not, most of the time you don't need charges. You want the biologically relevant, and most of the time you choose the default one. So default for the last one is C terminal. Default for the first one is called N terminal, unless there is a glycine, because glycine then it has to be a GlyP and so on. For special residues like a proline and stuff, you have a special. So that's the first step you are going to do. Choose the two terminals. And the good part about CharmGUI is they do it for yourself, but you need to do what it is doing, right? This is an assumption that if you overlook and then you go down the road and you say like, oh, I wanted something else there, then it's too late, okay? So you have to first, okay, so that's the first part, C-ter, N-terminal. Okay, then is preserved hydrogen coordinates. So why is that important? So an X-ray crystallography has a resolution of the order of 2 angstrom, typically 3 angstroms. A hydrogen atom is of the order of 1 angstrom or less, right? So if your X-ray crystallography does not have a resolution of 1 angstrom of that order, you do not see the hydrogen. You cannot see the hydrogen. But if you do have that resolution, even then you do not see all the hydrogen, because some hydrogen will be fluctuating, right? So by preserving hydrogen coordinates, it's saying like whatever hydrogen we see it in the experiment, should we keep it or should we not keep it? Okay, that's the next option. If you want to keep it's advisable that you keep that hydrogen. If you do not keep that hydrogen, then down the road, we're going to model those hydrogen, and those hydrogen modelings are very accurate. So you don't have to worry if the hydrogens are not there. For an NMR structure, the hydrogens are all there because NMR structure is distance constraints. They do not, the resolution is not in the same. So in NMR structure, you'll see all the hydrogens anyway. I'm going to ask these questions to others. Well, mutation is pretty easy. Okay, what is the next? What is the protonation state? Anybody? What is a protonation? When I say protonation state, what does it mean? Okay, one at a time.
Maybe adenation of H plus ion, cation.
Any other answer? Charging the protein. Okay. So in a protonation state, what happens is you have 20 different residues, okay, and they have charges that are defined at neutral pH. So whenever somebody says like this one has charge this and that's charge that, they're defined as neutral pH. As you change the pH, the charge of the residues are going to change. And that's called protonation in the sense that in which proton configuration that I have. The things that you have to worry is mostly histidine, because histidine has a different charge configuration at the neutral pH, very close to neutral pH. Okay, so when you say protonation state, you have to worry about the histidine. You have to know like which protonation state do I have. But for most other residue, if you're doing it in neutral pH, you don't have to worry about it. Okay, so next, let's protonation state. Oh, yeah. So there are some few options is given. Which one? Okay, disulfide bond. Anybody knows what is a disulfide bond is? Great, easy answer. Cysteine. So in a crystal structure or thing, most of the time the disulfide bonds may not be present. Sometime or something. So then you may have, well, even if it is present, it cannot be read from the PDB file. However, it's written in the PDB file. In that case, you have to manually say, like here, if you click on the disulfide, maybe there is no cysteine.
No,
here.
there is no
cysteine
bonds,
here.
yeah.
But if there is a cysteine, you click and you have to manually say connect these two disulfide. Okay. I think the next part, those are phosphorylations, the only other team. So what is a phosphorylation? Okay, good. And what does it do? Huh? Yeah, but what does it do physically? What is, okay. Well, yeah, it changes the charge and yes. So there are a few residues that can be phosphorylated. So you have to click which residue you want to be phosphorylated and so on, okay? So those are the options that it choose. The other options, we are not going to go through it, except, let's see, if you go slowly, okay, the model loop part. So you see, sometime in an experiment, this is an NMR structure. So it is, you have all the atoms coordinate, but sometime in X-ray structures, you might be missing some coordinates. And most of the time, the coordinates that you miss are for the flexible part of the protein. That's called loop. And if you are missing those coordinates, it's asking, do you want to model them? Okay. And it will do it. And loop modeling is a very difficult task. I would recommend if you are missing more than 5 or 6 residues, then don't trust the modeling. Maybe you can trust the modeling up to 10 residues or something. Okay. The program that it uses is Modeler, is one of the older program. So if it is more than 5-6 residues are missing, don't use it. Download an AlphaFold structure or make a full prediction with an AlphaFold structure, and we'll go through an AlphaFold later down the road, and then upload that. Okay. So just if you are missing, don't model with this one for more than 4 or 5 residues or something. It's not going to give you a correct result. Okay, I think that's all. Okay, next go generate PDB. So we'll see another,
yeah. Yeah, you can see that it's running in the computer.
Okay, something is wrong. Let's see what is wrong. So whenever you see that sign with a what do you call skeleton and that sign, that means something. That's the charm danger button. Okay, so if the charm output last line has that means something failed miserably.
Yeah, it means that you have configured your settings badly, actually.
Yeah. So does it say what it, okay, let's see.
Yeah.
Okay, go down a little bit and let's see what is it happen. Yeah, so, and a little bit up, let's see the last error message. Go a little bit up. And right here. Okay, yeah, right there. What we did is, I think you clicked the phosphorylation button.
Yeah.
And it couldn't find that residue phosphorylation. So we should, it said like the residue for phosphorylation you chose is not a viable one. So we need to unclick the phosphorylation.
Yeah, let me do that once again.
Oh, no, not removing. So in a crystal structure, sometimes the coordinates of a loop may not be determined. So what you will see is like one chain, all the coordinates are there, then 5 residues there, there will be no coordinates. It will say missing residues, or they will just taken away from the PDB. So let's say 1 to 10, you have coordinates. Suddenly the residue number will jump to 14, and then you'll have coordinate again. So that means 11, 12, 13s are missing. But when you are doing a simulation, you want the full part. Otherwise, those 2 parts will just go away. So, and that's why it's asking, like, if you are missing residues, that means like certain residues coordinates are there. Do you want them to be modeled? Yeah.
Okay. The next bit is the it generates a PDB for charm input. I mean, for you can use it for other molecular dynamics package also.
Okay, so before going to the next, there's the first quiz. Okay, are you guys all over here? Are you here on this page? Okay, good.
Oh.
Oh, let's see what's the error there. Oh, I think the phosphorylation should not have been clicked.
Yeah, just unselect all those options.
Yeah, don't put any options, just
Yeah.
go to the next. And then hit the next option. Yeah.
In CompBio, you can do a lot of manipulation, but if you don't know what it is, best will be to skip it.
Yeah. Okay. Okay. So let's wait on this page. Let's see if everybody's on this page. Then we have the first quiz, okay, from the first lecture. Okay. So if you go down, go down here, right there. So there are some terms there, right? And that's fine. Okay. There are some terms there. So the way that it is organized is like you have the header, it's called energy, and the value is here. Delta energy, you don't have to worry. You have the bonds, the value is here. You have the angles, you have the van der Waals, and the values are here. Okay, so that's like, okay, the first question, if the energy is larger, is it better? Or if the energy is smaller, is it better? Good. Why? Wow, you all are smart. Great. Okay, that's the first question. Second one, when I said, in my lecture, something related to bond, and you see an energy related to bond there. So what was the bond energy? What was let's say, when I was representing a bond, how was I representing? What did I put between 2 atoms? A spring, right? A spring. So that is the energy of a spring. Okay, so all the springs that are stretched and stressed, that energy, all of it, added for the whole system, and it's been put right there, bond energy. Okay, van der Waals, and so on, and then electrostatics. So if you look at this one, your system should be at a negative energy or very low energy. Okay, so when you start with an experimental structure, a lot of the time, what we call stereochemistry, that means like the atoms are not properly placed. They place the backbones and the side chains as best as they can, but they may not have the right bond length, the right angle, and so on. And that's why a structure that you take from a experiment, the first step, you'll see the energy is high. In this case, I have 21,000 energy, most of it is coming from the angles. 17,000 of it is coming from the angles. So that means like in these structures, the angles between different atoms were not optimized, okay? So this is the first thing you see is like, my angles are not, and we'll do something about it. And the other part, what is the unit of energy? Kilojoule per mole, good. Okay, we'll go with the kilojoule per mole. The unit of energy here is kilocal per mole, but that's okay. We can multiply by 3,000 something and we'll get, okay. So that's it. Okay, let's go to the next.
Okay, so next you have to download it. I mean, there's nothing to work for now.
Well, if you zoom in, I can explain what are the different files. Okay, so let's look at the different, if you download it here, you'll get the different files. So the we have two chains. It's giving the individual files for each chain, and this one is the file for the whole protein. Okay. The first one is like the input file, charm input file, and don't worry about it, because if you are not a master in charm, you'll get lost into it. Okay. And charm is, yeah, I mean, like charm is, because it is the oldest one, it is the junkiest one too, but it is the most versatile, you know, I shouldn't say, I'm like Karplas's student. Okay, I shouldn't say these things. So Martin Karplas wrote initiate the charm. So, but it is very, it's not user friendly, but it's very versatile, very powerful for people who knows it. So don't worry about it. But if you, someday, if you want to look into it, what's happening in this file, that's the first file where it reads the PDB structures. And then this is the output file. So charm input file should have a .inp and .out is the output file. And then this is the structure that came after the charm manipulation and so on. And these are the two things that you need to carry forward. .crd means coordinates. And once you download, we'll look into a file. How does it look? And .psf means is called protein structure file. What it does is it takes a molecule and say like this molecule looks like this molecule in my force field parameter. So I'm going to like this oxygen looks like, because in force field parameter, you'll have 16 different kind of oxygen, depending on where the oxygen sits. Does it sit next to a carbon? Does it sit next to a hydrogen and so on? So you look into that and say like, okay, this oxygen looks like my O13 in my parameter file, in my force field. That makes that connection, okay? And so we'll look into that a little bit. Okay, so you want all of us to download this file?
Yeah. Also, the .psf file, it contains the bond angle and some other.
And the .psf file also contains which atoms are connected with each other by bond, which 3 atoms are connected by bond, by a triangle, which 4 atoms are connected by a dihedral. But you don't have to worry about it. Just know, because as you get more used to it. Again, this is a multidisciplinary field, so don't worry about the overwhelming term.
Yeah.
Just get used to it.
Yeah, you can download this file, or you can view structure from here if you want to see it. Yeah, you can see that only one model is chosen from the NMR. So yeah. Just download it from here.
So after you download, let's look at some of the files.
Okay.
Okay, how many have you seen a PDB file before, like got into the PDB file and seen it before? 1, 2, 3, 4, 5, 6. Okay, so we'll have a quiz coming right now. We'll see. Okay, let's open the whenever one GZ.
Yeah, it's not downloaded yet.
Okay. What happens? Dot PDB file click karo ki hoy? Individual file click karo. Eta destruction.
কোনটা? এটা?
Dot PDB file click karo ki hoy? Okay, I can take it. Okay. Wait a column. No, text file.
Oh, text file.
Okay. So in the PDB file, well, Nilima, what are the different fields? What does the first one say? The atom. So, okay. So, well, I'll answer. That's it. The first 4 letters tells an atoms. Atoms means those are atom part of the protein molecule. If an atom is not part of the protein molecule, it will have a term called het atom, that is heteroatoms. Okay. So those are the distinctions. So first you will see, first is to be listed all the protein atoms from the protein molecules. Okay, so you'll have the atoms. That means like they're part of the protein molecule.
Yeah.
Next, you
actually, let me show another PDF file where it contains the het atom. Yeah. Okay. Yeah.
Okay, so this is a PDB file where there is no protein
Molecules
in it at all. It is a PDB file where everything is heteroatom. So that means like they are not amino acid. Molecule belongs to amino acids. Okay, now let's go to the first one first. Okay, so next is the serial number of atoms, like 1, 2, 3, 4, 5. And then the next is the type of atom. Like the first atom is nitrogen, second atom is carbon alpha, third atom is carbon, fourth is oxygen, then next is hydrogen, and so on. Yeah. So can you show? Yeah, actually, good question. Let's show.
Yeah. Okay.
In the download folder.
Oh, okay. So first you have to uncompress it. I mean, you have to. You can use. Yeah. You can unzip it using tar command, or you can unzip with your file explorer. I mean, if you use tar, then you will have to use xvzf. Then it will be uncompressed, and you see your files here, or you can use your file explorer and tell it to extract here. Then it will create another folder and uncompress all those files in it. Okay, let's see what it contains. So in the topper folder, it contains all the force field, I guess.
Yes.
Force field and parameter files actually.
Let's go to the, let's stop here and see what are the files. Okay. So this is where all the files are, and .cif means like that's the all PDF file. I think that Charm GUI website was showing all the files, and then you have individual chains and input file, output file, and then So we were looking into one of the PDB file. That's what we are looking into. Let's say .pdb, and we wanted to check what's inside a PDB file, because that will give you an understanding what's the MD simulation is doing. So if you open the PDB file again, okay, so yes, yeah. So if the first column is atom, that means like it belongs to protein. Second column is the serial number of atom. Third column is the atom type. That means whether it's a nitrogen, carbon, and so on. The fourth column is the residue name. So glycine and so on. And then the residue number. Okay. And then is the coordinate. And that is the most important part. That all the coordinates of each atoms you have the X, Y, and Z, 3 values, X, Y, and Z. Okay, the first 3 values. And that is all is coming from the experiment, right? Coordinates of the different atom that you have to experimentally determine. And this is the most important part. You know, you have to spend $50,000 to get those coordinates or even more, right? I mean, to run an experiment. So, and that is what we carry on. These are like, and carry on to do an MD simulation. So this is the PDB format, which PDB format, because it started so early, it's changing because not all the fields have enough width. Like you can see the decimal places are only 3 decimal places. And that's not accurate enough for a computer to store. You want to store 10 decimal places or something in a computer. So we have an equivalent file in that. That's called .crd, a coordinate file. Let's open the .crd file. It is a similar file, except the precisions are way bigger. Well, like here, you can see saying first you have the serial number of the atoms, then you have the residue, and then the atom, and then you see the same coordinates, but you have you have lots of more decimal places because that's what you need for a computer to, the accuracy to be higher. So that's the difference between the PDB and coordinate file. And once you have transferred a PDB formatted file to a coordinate file, from now on, the MD simulation will use the coordinate file because it has a higher precision and so on. And actually, you can keep them in a binary format too. That means like, this is a text format where you can read. A binary format, you cannot read, but you can keep it in a high. Okay. And
oh, sorry.
Yeah, and Rahat was telling all the parameters file, force field parameters file, and so on. That's under the topper directory. It's a very busy directory. If we get a time, we'll look into a force field parameter file, how it looks. But for now, let's follow on with Rahat and yeah. So
yeah, so you don't need to worry about this topper folder. Just forget about this actually for now. Okay, so after that, you can manually build your input files for MD simulation, but there is another nice feature in the Charm GUI, which is called Solution Builder. I want to I want you to go to the Solution Builder option actually. Okay, so what is Solution Builder? Solution Builder is a feature, or should I say a pipeline which just execute all those commands to make an input file for molecular dynamics simulation. So if you go to that page, you see that some options are, some description are written here, and what it does for making those molecular dynamics input file. So you can, once again, you can download your PDB file, or if you know these RCSB number, you can just write it here.
Do something, because you already downloaded the coordinate file. So let's upload a PDB in that web page. Let's go to the channel.
Yeah. Let me.
Yeah. No, no, don't click the, okay, yeah, go ahead. Click the coordinate file that we just generated. Pick up the coordinate file. To borrow karo to এটা
তো বড়
হয় না এটা না তোমার যে এটা ঠিক আছে
তো বড় হবে না
ওইটা বড় হবে okay so here you have to browse the .crd file that we chose and we created last time. Let's browse that file and click the option charm, because that was generated by a charm. So let's browse that .crd file where you downloaded.
Yeah, you no, I don't have any option to zoom in. So
because we'll walk around and help you if anybody. Yeah, let's pick, and then choose the charm option there because it's not a PDB format.
Yeah.
Okay. Well, is there, everybody get to upload the .crd file? So what we are doing is like, because we already transferred the format from PDB and to coordinate, we don't, .crd format, we don't have to go through all the steps again. So we are uploading directly the coordinate file. We are letting it know that it's a charm formatted file. Okay, so let's hit next.
So as we have done all those manipulation and it's not actually giving us many options here, and now the page is actually blank. But if you upload the PDB file, you'll see that the file manipulation part, which we have gone through for now, it will pop up here.
Oh, so it says like some files are missing. Maybe you have to start with the PDB file?
We have to
start with the PDB file. Okay, that coordinate file will not work. Okay, let's start again. Sorry. Yeah. It says some files are missing. So let's start over
okay.
again.
So we have to start with the PDB file?
Yeah, we have to start the program.pdb, not coordinate file.
Okay.
In that one, yeah. Let's choose the.
Where is it? Okay.
Yeah, let's choose the PDB. Yeah, the A or B PDB, whatever chain you want to work with. Or step 1 PDB. Is there a step 1? Yeah, that one. Step 1.pdb, the 1, 2 before.
Anyone will be fine, actually.
There is no PDB there. Up.
Oh, yeah.
Yeah. So let's choose the step 1 PDB, that whatever, and then choose the charm format there. Yeah, the coordinate format will not work. You have to upload a PDB format. It works in your laptop? Okay, good. Okay, good. Okay, so for some people it works. That means yeah. If it doesn't work, pick up a PDB file.
It works for them.
Okay, so you are working with a different PDB file. Oh, you are working with one.
The same one.
Oh, okay. And let's see what the option is showing. Click on the chains you want to select. So it's showing a lot of chains. How did that happen? Oh, did you choose? Let's go back. What did you? Let's go back one more time. Let's see what happens. Okay, so here, if you choose the .cif file, then you have to choose the option PDB format, the PDB, because .cif is a PDB format, and it's a PDB formatted file. But if you choose that step 1 PDB reader.pdb, that's a charm formatted PDB file. So that's why yeah. Still showing that.
Someone is correct.
Okay, so let's go back. Let's do another thing then. Let's choose the another, not the .cif.
Can I choose this one?
Not charm GUI. Whatever.
Choose this one.
Yeah, you can choose that one.
Yeah, so download this from
Yeah. So choose that one. It's a .gz file though. It's not going to work. What did you
upload it? I downloaded it from here.
Oh, it says .gz. Okay, let's try that. No. Yeah, because well, I think what happened, that was a zip file. It's not a PDB. So let's go to the download again. That RCSP. RCSP. You said download files, and then you choose the PDB format. You chose the PDB GZ. GZ means zipped. So you're going to choose that one. Yeah.
All of you guys, did you able to upload the PDB file. Nice.
Yeah, let's give me we'll walk around and we'll go to.
Okay, okay.
Okay, there you go.
So as you can see that we have done these steps
Wait,
before.
Does anybody need help? Okay, good. Go. So, okay.
Okay. So as you can see that we have already done those PDB manipulation. I'll just go to the next step. It will pop up all those options we have worked so far. Oh, it has nothing. I mean, we have done all those steps before. That's why I'm skipping this. As you
Okay,
can
so
see,
this is the part that's new
Yeah.
now that we are doing.
yeah, actually it's not new. I mean, you have seen this computed energy part
at
before,
the bottom.
but the part
Here.
down is new. Sorry? Yeah, you'll just upload the PDB file and just click next.
Oh. Okay, so next, this is the new part.
Yeah.
So here, so we have to choose a, how big we want the water box to. That means how big we want how much water we want to put around the protein. So there is a trade-off. The more water we put in, the system is bigger, it will run slower. Okay. Less water we put in, we run the risk of system of not being biological. Okay. So the minimum number, okay. Does anyone know what is the width of a hydrogen water molecule? Or what is the volume of a water molecule? Okay, so volume of a water molecule is roughly 30 angstrom cube. So that is like 3 angstrom times 3 angstrom times 3 angstrom, roughly 3 angstrom on each direction, right? And it has been it is a wonderful experiment shown that the 3 layers, at least 3 layers of water molecules around a protein follows the protein behavior rather than water behavior. So what it means, in water, the waters are random, semi-random. Like if they are gas, fully random. In liquid, kind of semi-random. That randomness is less if the water is next to the protein. So when you're thinking of a protein, you can almost think of a protein with 3 layers of water. So that's why if you want to be biologically relevant, you'll at least put 10 angstrom so that of the 10 angstrom beyond the protein, so that you at least have 3 layers of water. Otherwise, your protein will be not biologically relevant. Okay, because in reality, the protein moves with at least 3 layers of water around it. Yeah. So
also, it should be larger than your protein size, I guess.
Well, it says that, no, let's check the next box, not the specific. Yeah, so this one says like the edge distance, that should be at least 10. But I personally go to 15. Okay, the reason is, so we, in this one, what we call, we do not simulate a finite system, what we simulate an infinite system. What it means is like, we build a copy and that copy is being repeated every time. It's an infinite system. Okay, so it's called periodic boundary. That means like every certain time the same thing happens again. So that, if the water on the edge they do not evaporate. If you leave water in the glass, at the end of the day, your glass will be 80%, 20% gone, water is gone, right? There's evaporation happens. That because at the surface, the water molecules has nothing to bounce back from. It will jump up and say, I have empty space, it will fly away. So that's the evaporation. That will happen in the simulation too if your physical parameters are right. And you don't want that to happen. That's why you simulate an infinite system, in the sense like we have our box and we repeat it, and repeating does not cost because we are just repeating the same thing. But it has a trick. If I repeat it, if I say my box has 10 angstrom beyond the protein, so it's my protein box, and you should use that fit, to size to protein, use that option. Okay, don't specify the water box option. Then you have to know the absolute size of your protein and so on. So the protein may change its conformation, then it may interact with the protein in the neighboring box, and you don't want that. Okay, so that's why you want the width to be large enough so that one protein does not interact with the protein in the neighboring box, but not too large enough that your system gets too big, then it becomes slow. So at least 10 angstrom. If you go below 10 angstrom, you are not doing biological. I typically put 15 angstrom.
Yeah. So 15 angstrom is good, I guess. Okay. Next option is the add ions option. So you can add.
Each protein molecule will have a charge. Okay, each protein molecule typically will have a charge. But in solution, you don't want charges. So you have to neutralize the whole system. Why don't you want charges? It's because electrostatics is painful to calculate. So if you have charge, it's more electrostatic. So you want your system to be neutral. One way of doing is neutral is if your protein has +2 charge, put 2 minus negative ions, whole system. So your whole system will be protein +2 charge, water, and 2 negative ions. So that's one reason to put ion to neutralize. And it has different ion options. If you put KCl, or NaCl, those are the two. NaCl is the salt. Those are the two most options. The other way is like if you want to replicate if you are using, sodium chloride, if you want to replicate the salt concentration of your cell, it's like 0.15 molar or something like that. So you'll be given two options, right? One is what atom types to use, and the other option is what concentration. Okay, so let's choose the NaCl. We can get rid of the KCl part. Yeah.
But every time you add or remove a ion, you have to calculate the solvent composition.
Wait, we'll go there. So you'll have two options there. Neutralizing, the first option means like you're going to neutralize the whole system. And the second option is the concentration, what you want the concentration to be. Okay, and the 0.15 molar is probably the cell concentration. That's typically you do the simulation too. Okay, so after you've chosen that, now you calculate the solvent composition, then it will say like, for my system, I need to put 28 sodium and 26 chloride. See, there is a +2 difference there. The +2 difference is to neutralize the protein, and the remaining 26 is to maintain the 15.15 millimolar concentration. Okay, so now I have a system which is neutral, whose salt concentration looks like a cellular salt concentration. So move forward. Okay. So it may take a little bit of time to run these. And we are going to take a break after this step. So after this step, what we have done so far is like we took a protein, we solvated it, we are going to solvate it, we put the proper terminals, we put the ions, and we put the water, and we have connected it with the right parameter files. So that's what we did. And how long does it take to run?
Maybe
Okay. So
5 more seconds.
we can take a break now.
5 or 10 seconds, I guess.
Okay, so it says like there are only 2 more steps, then we'll finish this part and take a break.
Yeah.
Any question until, while we are waiting? Or is everybody's one is working? Somebody is not. Oh, okay,
not
let's see.
working?
Yes. NaCl choose to down. And add, yeah. Oh, more iron types. Add simple iron type, add good power. Calculate solvent composition. Solid composition, okay, 32, 31, then next.
Okay.
Oh, yeah, let's wait. Is
It's
it
done. Okay.
Oops.
Has everyone been able to do the steps?
Okay. So there is a question here is like crystal structure resolution is supposed to be good at below 3. Why is that dogma? Why does it have to be below 3? What does it mean? We'll answer that. Let's finish, we'll answer that for everyone. Let's finish. Okay. So this is the next step. And at this step, what you are looking at is this part I will ask you to ignore because there is like too much mathematics going on in the sense that, electrostatic field is called infinite field in the sense like ideally we should feel an effect of an electric charge, even if it is like 10 miles away, there's some effect because 1 over r square, it goes very slowly. So you cannot calculate that efficiently just by 1 over r square. We have to use special methods. And that's called, Fourier transform methods. And so it's just saying like, how do you want to do the parameters of the Fourier transform and partial mesh? Just click the generate grid. Don't go for messing it up. Just use that. This is what it is saying. Like we are using this efficient method for electrostatic calculation. What parameter should we choose? Okay, so let's. If you look at the energy there, it has already become negative. So that means like our system is getting, and this is going through a minimization. That means like it's a step where it tries to minimize the energy by, it's called gradient descent, like by calculating movement that will minimize the energy. And you see like it's calculated at step 15, it was negative 98,000. At step 20 is negative 101,000, is still going down. So our system is getting more stable. If you run a MD simulation with an unstable system, it's going to blow up in half an hour because there are inbuilt checks. If your MD simulation energy jumps high, the MD engine will just stop. There is no meaning of running it. Okay, so if you do not start with a really stable system, you'll see your MD simulation just stopped, and you wasted that amount of computational resources. Okay, this is the last part, and this is the most beautiful part of Charm GUI, in the sense that we did all these, and we can download it for any of the program we want to run. And trust me, each program has decided to make the input file so different from each other so that you cannot take one input file and run into another. In the sense like, if you get an NAMD input file and you want to run it in Charm, it's not going to work. If you run into GROMACS, it's not going to work. Not only that, I grew up using charm. I have difficulties understanding GROMACS input file. It's just different. People came and they said like, between our friends, it feels good, let's go on. And then it becomes a trend, and that trend just stays there, but it's so hard for other community to understand. And it's a pain, but Charm GUI does it awesome. You can choose which input file, MD engine input file you want. You can choose all of them if you want. Okay, and two of the MD engines that we are going to use is NAMD and GROMACS, right? NAMD and GROMACS. Yeah. So, but if you have access to Amber, if you have access to something like, somebody told me that in Bangladesh, certain kind is very popular, like Yasara or something. I don't know. Yeah. Okay. And Yasara and Desmond. Okay. So I don't see an Yasara there, but Desmond is there. So you can download MD input file for anything that you like. So click those things and that whatever you want.
Yeah, I'm just using the NAMD and GROMACS option.
Okay, so then there is the next part. Okay. You don't worry about the NVT, NPT ensemble. Those are like briefly in NVT, your volume is fixed. And that's where you want your system to run in the beginning, because if you do not fix your volume or temperature or pressure, you have to connect it to a supply. The errors can be hidden. It is hard to understand the errors if you do not fix your volume and number and temperature. So the first part, that's why is NVT, so that if any problem arises, you understand that that's called the equilibration. And once the equilibration is done, then you can put a special pressure, because now I know my system does not have any error. So now I can apply pressure. Okay, so that's the reason. Just follow those. But the important part is the temperature. Okay, and that's what you need to choose. The reason that default is given 303 degree Kelvin, that's because all the force field parameters were developed for that temperature. Because remember I told like force field parameters wants to replicate the solubility and viscosity and so on. But as you change the temperature, the solubility is going to change. So those parameters were actually developed to replicate at that temperature. So does that mean, so if you put like, let's say 100 degree Kelvin, is it going to work? It's going to work with a migraine. Like it's going to work like barely. Okay, so you don't want to calculate the biological effect at that temperature. But if you want to calculate, instead of 303, if you want to calculate 330 degree, there is a good probability it will work, because most of the parameters do not vary that much according to the temperature. Okay, so unless you have a definite reason to change the temperature, don't change the temperature. And I personally do change the temperature, because sometimes my collaborators say like, I check that protein at 30 degree, at 70 degree. 70 degrees is a good number, because that's where all the bacteria gets killed and so on, stuff like that. I check this protein at 70 degrees centigrade, which means like roughly 343 or something. Then I do run that at 343. But unless you have a good reason, don't go beyond much, because remember the parameters were developed for that temperature. Okay, so that's, yeah.
Yeah, so now the input files has been generated, and all you have to do is to download the tar file or compressed file from the option right here.
Okay, I think, this is amazing. It took me like 3 months to 4 months to run my first MD simulation just to start. And you're learning it in a day. So it's like, there's like so much that the thing has advanced so much. And I remember, because I moved from I was physics and moved during my postdoc to do these things. I remember I was running a virus simulation. And whenever you run on it's good practice to run multiple copies of a simulation so that you have a statistical confidence. But each copy should be different from each other. Okay. And the way you make it different is like you put different random seed in the beginning, random number in the beginning. And I didn't do it. Okay. So after 6 months, or like 4 months, I see my simulation. I see like, man, my 5 copies looks identical to each other. Like, the end structures are totally identical. Like, how did that happen? And I go back, I put the same random number seed in the beginning. Okay. And then my 4 months work was gone. So I have to start it was like nowadays it's so easy. It's like, put this thing, you get, by the end of the day, you are ready to run. It's like, okay, so we downloaded.
Yeah, it's downloading. It's not downloaded yet. In the meantime, I was trying to visualize the output PDB file, the solved PDB file, but I don't know, maybe.
Okay, I see. Are we? Okay. Put a file that so আমরা এখন break নিতে পারি, এটাই তো last step.
Yeah, I think.
Yes, I think
that-
why don't we take a break because it's taking a little bit of time for download, and I think second part is like take these files to the Ohio Supercomputing Center and start an NMD simulation and so on. I think that
Just submit those files. Yeah.
Yeah. So, okay, I think there's a tea or some kind of snacks outside. So we gather at 11, 17 minutes break. We gather at 11. Okay. Yeah. Thanks.
বন্ধ করে দেন। ওর সাথে কিন্তু কত এমবি ফাইল? 150 হবে, 150 তাহলে ঠিক আছে। এটাও তো 1 মিনিটের মধ্যেই ডাউনলোড হয়ে যাবে।
Battery charge. Okay, before we start the next session, there are a couple of questions, and I think like I wanted to answer it for everybody, so that helps. So number one question is like, if you are choosing a PDB file and if you have to look for a resolution, what should you what resolution should you look for? Basically, the question, I can rephrase the question: what does resolution means? Okay. And the answer is, it's not a straightforward answer. The reason is, it depends on what you are doing. Okay. If you're in X-ray crystallography, if you can go to higher and higher resolution, that shows you the skill you have. But that does not mean that you are capturing a biological relevant information. Okay, and I'll give you an example one. So let's say we have a protein. I'll draw a simple protein, a helix, and another helix, and connected by a flexible loop. So secondary structure, if you know, I'm assuming that you all know about the protein structures. So if you have two helical structures and the loop, this part will be very rigid, like not rigid, like not fluctuating as much, versus the loop will be fluctuating a lot. So now if a crystallographer comes and made some, you know, the crystallographic, it made a crystal, when it solves the crystal, it may have only these two structures. Okay, why is that? Because crystals are typically done at -100°C or so on, right? So at -100°C, you can reduce the fluctuations of the rigid part, but you have not reduced the fluctuation of the flexible part enough to be able to get, well, so when I say you got this part, experimentally, what you actually get, like so this is the experimental, you get a Fourier diffraction. From the diffraction, you can calculate some density. You'll get a density, very well-defined density, you know, for the two helices. That's what you're going to get. And then you're going to get a blob, like in the sense like you're going to get like some blob like that. Okay. So what it tells is like, I can fit my model here because they are not fluctuating a lot, but this loop is fluctuating so much. So that's why I have density everywhere and I do not know where the loop is. Okay, so that's what it says. And then, so if you calculate, so somebody came and this one, they have a resolution, this part, a resolution of, let's say 1.5 angstrom. And this part, they have a resolution of like 5 angstrom. Okay, because it's not because it's a bad experiment, it's because that's the thermodynamics. The thermodynamics of the flexible part is 5 angstrom. So if you make an average, maybe it will come to 3 angstrom. So when you look at the PDB file, you'll say like, oh, my 3 angstrom. But if you go deeper, you'll see if you can download the density file, they should have a density file somewhere. You see like, okay, certain regions has very well-defined density. Certain regions do not have well-defined density. So your average is coming down. Okay. Does that mean it's wrong? No, because what it is telling is like, this part is thermodynamically constrained. This part is more fluctuating. Now, another group came, they made a mutation here, let's say, and did the X-ray crystallography, or they use certain other kind of solution to make it less stable, or something they did chemically. And they did an X-ray crystallography, and they get to see the whole part. Okay. And now the average one, let's say, went down to 2 angstrom. Okay. But did it give me any more new information? Or did it take away information from me? Which one is more informative, this one or that one? What do you think? Huh? The upper one, right? Because I have the information of thermodynamics here, right? I do not have the information. So you have to read the paper carefully to see, like, every paper will have certain options like, I did this, I did a mutation here, I did change here, so that I can get a stable structure. And then you decide which one will be relevant for your project. Okay, so that's the first part of the resolution. So, and this is an X-ray structure, right? And the NMR structure does not have any resolution. What you are going to see, NMR structure is equally a valid structure, because NMR structure, what you will see is like how many distant constants were violated. They won't have a number to it, okay? So that's a whole different story. And then the cryo-EM structure. In the cryo-EM, you'll have a resolution, but the resolution in cryo-EM has a total different meaning. In X-ray, resolution means like I'm sending a 3 angstrom wavelength. Ideally, I should have a 1.5 angstrom resolution, because a wavelength of light can see 2 things. So this is the wavelength, lambda. So anything lambda by 2, this wavelength can see it separately. Anything less than lambda by 2, they cannot see it separately. Okay. So in X-ray, it's very simple. Your wavelength is 3 angstrom. You should expect a 1.5 angstrom resolution, but because of thermodynamics, you don't have that resolution. So, okay. In cryo-EM, it's totally different, because cryo-EM, there is no physics student here. I cannot ask this physics question. That's like, Shishir, you have it. What is the wavelength of an electron? That's too much. Okay, so X-ray wavelength is of the order of angstrom, right? So wavelength of an electron is of the order of femtometers, because electrons is heavier. So you can, so ideally, so it's like of the order of 10 to the power minus 15. So ideally, you should be able to see things of the order of 10 to the power minus 15, like almost to the size of an electron, with an electron microscope. But the problem with the electron microscope is electrons do a lot of radiation damage, right? I mean, you can survive 100 X-rays in your life. You cannot survive 100 electron X-rays in your life. You'll be mutated. So, and that's why where you can send a lot of X-rays to get a structure, typically you send 10 electrons, just counting 10 electrons to get a picture of a molecule. The reason is like the more electron you send is going to get radiation damage. So the electron microscope, the resolution does not come from the wavelength. It comes from the uncertainty, because you are sending 10 electrons. There is so much noise. The more electron you can send, you get better picture, but then you're damaging the system. So it's from the statistical uncertainty. So that's a different meaning of resolution. Again, so the resolution has different meaning on different fields. Don't get bogged down by it. And if you do a modeling in AlphaFold, so that was the question, that if you do not have a protein structure, we'll have an AlphaFold session on the 3rd day. Now we can confidently build structure of a protein just to computation in a matter of hour with as much accuracy as the experiments, okay? So if you do not have a protein structure solved, use AlphaFold, and we'll have a session on the third day on that. So that's, I hope like that solves the resolution question, because the resolution, it depends on what information you want to extract from it. I personally don't mind having somebody has 8 angstrom resolution, because what it tells me is like 8 angstrom means like, this part has 2 angstrom, this part has 5 angstrom. I know which part is moving, mobile, which part is not mobile, because I'm going to do MD simulation, right? So I personally do not mind, because that gives me more option, more information. Yeah, so it depends on, but a crystallographer, like now I need to know everything. I mean, it depends on who you are asked. And then another question was like, if I have missing, like this structure, if it is, this part is missing, okay, what do you do about it? If you ask me 2 years back, I would say go model with something. Since 2021, I said, don't worry, run an AlphaFold, get that structure, go with it, okay? So the whole field has changed. So 2021, if you are missing, just use AlphaFold, get. And the third question is, I think like you asked, like somebody says like, I have multiple PDB. Why did I choose, or for the same protein, why did I choose that particular PDB? And that questions typically come when you are doing some kind of binding calculations. The reason is a protein may change conformation, okay, upon binding, before binding, or so on. And when you are doing a experiment, computational experiment to calculate binding, you have to convince yourself that you have the right conformation of the protein to calculate the binding energy. And so if your reviewer asks, why did you choose? That will be like, oh, I know these because this is the binding conformation, or the protein does not change conformation due to binding. That's why I'm choosing it. Otherwise, it's not a valid, you just try, just a trial, right? Okay, so again, when you have multiple entries for a PDB, read the papers. Read the papers, like 10 steps. Third step was like read the literature, because like what other people did. So read the literature and see what they did so that you can pull out the information from there for your own project. Okay, if any other question, you can answer. Otherwise, we'll go to the next part. Oh,
Okay, so I guess everyone done with the downloading part. Has everyone downloaded the parameters or input files? Okay, great. Yeah, so let me just share my screen first. So let me just show you what kind of files are in the Charm GUI folder. So this is the whole project files. I mean, we have all the GROMEX and NAMD files here, also the force field files. What we'll be using is the NAMD input files for today. You see the input files here, also the other files which have described Dr. Amit before, like CRD, PDB, and PSF files. We will be using step 4 equilibrium.inf and step 5 production inf file for the NAMD MD simulation. Before that, I want to show you the step 3 input PDB, I mean, the solvated protein files. Okay. Are we just using VMD? Okay, so before solvation or before, okay.
Yeah, we'll have a VMD session on the boat. Don't
Yeah, but,
worry about it. You don't have to learn VMD now. So he is just showing.
Yeah, as you can see that these are the water molecules in the box. And if you, I don't know if you can see it, but there's some protein molecules in here.
Let's make the background.
Yeah.
Yeah.
Oh, okay, okay.
Yeah.
Background gradient.
Okay, yeah, downward.
Okay. Yeah, so you can see the water molecules, also the protein molecules here. And if you change the graphical representation here, no, not new labels, like new cartoon. Now you'll see the proteins you have worked on, but you won't be able to see the water molecules. But water molecules are there, and we'll be working with these files for the next steps.
Sorry.
Oh. New cartoon install. Oh, okay.
Oh.
Sounds. Okay. So as you can see that we have added some sodium chloride ion, which are present here. Also some water molecules and proteins here. We will work with these files for the next steps. Okay, just for all the PDB file. So next step is to upload your files into the OSC. So first you have to log into the OSC Supercomputing Center website.
So let's give them some time. So
Yeah,
so log into the OSC account, and
that is ondemand.osc.edu.
and we'll, if you cannot log in, ask us, we'll help you if we can. Everybody has an account though, right? Okay.
Everyone done with the login? How many of you are not logged into the OSC website? Okay, let's wait for her. Everyone done with login? Anyone facing problem with the login? Okay, so I want you to go to the file section, and in the home directory section, you'll see your home directory of OSC supercomputer. Yes. It may be different from me. Okay, after that, we'll just have to drag and drop the folder we have uncompressed. Yeah, the whole folder actually. Okay. Oh, okay. Yeah, you'll just have to drag and drop the whole folder. Just drag it and go to your OSC file space. You'll see something will pop up, and you'll click on the upload 175 files or something like that. Okay. Let's refresh the page 1 second. Everyone done with the uploading? Okay. If you go to the folder you have uploaded just now, you see a subfolder named Chamgui something. If you go to that, you see your project files. If you go to the named folder, you see your named run file will run step 4 equilibration.inp and step 5 production imp in here. Step 4 equilibrations files are actually just minimize the energy for MD simulation first part. I won't be describing much about this. And step 5 is the production, or it's running the NPT simulation, and we'll get the results from these input files or these steps, step 5. So first step 4 and then step 5. Okay, and we are gonna need Slurm batch file for running this input file. I have created a Slurm file, default or template.
Okay, so how many have retained the knowledge from the OSC tutorial? What is a Slurm file? Do you remember, any of you? Okay, so you have the file that's going to communicate with the program NAMD or GROMACS, whatever you use, and those are the input files. But you have to tell the supercomputers, I want to run this input file with this MD engine for this much time. And that file structure is called Slurm file. Okay, so Slurm is going to do is like, is going to tell the supercomputer, I'm going to run which program, what input file, and for how long. Okay, so you'll be using Slurm for genomics, you'll be Slurm for modeling, like whatever you want to do with the supercomputer, you'll be using Slurm. It's a Unix-based file. And then the input files are just for the NAMD or the GROMACS. And just as a fun fact, the NAMD acronyms, NAMD, the authors never told this, the authors, Klaus Schulten, they never told what is the acronym stands for. But I think like they meant it not another MD simulation. Just like, because there have been, by that time, there are so many ways popping up, charm, and it's like not another MD. So that's the NAMD for, okay. It's pronounced as NAMD, not another MD simulation.
Okay, let me explain the supercomputing system once again. I mean, when you click on the clusters and open a new shell access, you are actually logging to the login node of that supercomputer. You can't submit or you can't work with those login node. You will need another system to submit your work. And that is what Dr. Amit was telling you. You will need a Slurm batch system, or you should think about it as another, what should I call? Another system for running your work. So you have to write a Slurm script to run your work on the compute node from the login node. I don't know if I can explain it clearly.
So do you remember the difference between compute node and login node? Yes, okay, so good. For those who don't remember, there are dedicated, like roughly like 100 CPUs or something, where people just log in from all over the world and they do their stuff. And then there are other nodes, hundreds of thousands, that can be only accessed from the login node. Login node can be accessed from anywhere. The other ones can be only accessed from the login node. So you are supposed to go to the login node and send your job to the compute node.
Yeah. And to submit your work to the compute node, you will need a system, which we are using here is Slurm. and we need a Slurm script for submitting our job. Okay. Oh, okay. So go to your job section, cluster section, and open OS shell access. You'll see a terminal view like this. Right.
So is anybody having problem with the terminal
having-
part of the OSC?
I'm having some trouble.
Oh, you having problem?
Yeah, I can't type.
Oh. You cannot type?
Browser type.
That's good. What, yes.
Oh, yes. It's just
Okay.
hang on. Okay. Okay, so if you type the command ls, you'll see your folder in it. That is, for me, it's charm GUI 3. I think for you it will be charm GUI. Can you see that folder? I think you can. If you type ls in the shell, you'll see your directory that that you have uploaded just now. For me, it's charm GUI 3, but for you it will be I think charm GUI. Can you see that? Right. Okay, so let me just copy some files. Right. Okay, this is the example bash script or Slurm bash script. This actually tells you how to tells the computer or the system how to submit your file or input file.
Yeah, but we have a problem here. I think like, how many of you know how to write an editor in Linux? Have you used VI or VIM?
Okay, okay. Let me just do another quick around. Okay,
yeah,
so
let's VI is a little difficult to learn, so let's use something else.
no, there's a workaround for this in OSC system. You can go to the charm GUI from file section and then go to the charm GUI. Oh, sorry. For me, it will be.
Okay, yeah, follow that one. That's easy to type. Whatever. So how do they get the step 4? Oh, how do they start a new file?
Let me look at that. Okay, so the step 4 or step 5 file, these are the bash script file. Actually, I want them to write the bash script file. I have included some instruction in the MD
Okay.
MD
Nice.
what was the file called? I can't remember.
Okay.
The hands-on file actually. So
so how do they start a new file in there?
okay, so if you want to start a new file, then you have to click here, new file.
So if you are following, you are supposed to start a new text file by adding that, by clicking the new file name and give it a name. And then you have to copy or type whatever Rahat is showing
Step
for your system.
Yeah, script dot. Okay. So if you want to edit that file, then you will have to go to the drop down menu and then select edit. Okay. So I want to open the hands-on file from Slack. But okay. Okay. So for the first 1, 2, 3, 4, 5 lines is just the sbatch command, and it's actually just some description like how many nodes you will be using for your work, how many times you will be using.
Let's go slowly because okay. So the first line, do you remember what the first line is called?
Yeah, if you attend the
okay, what is the first line called? Shebang, yeah. Shebang. Okay. So let's go. This is the, if you're using Linux, Unix first time, this will be your first Unix script, but Rahat has already put the structure. You have to just type and copy. So just type and copy. It's not a big deal. So the first line is the Shebang that basically tells like, we are going to use the script called bash under the binary directory to interpret this rest of the file. Okay. And then next, all the lines that starts with a hashtag sbatch, those are the lines, commands that is only for the supercomputer. Okay. So those are, you are specifying what are you going to use in the supercomputer, right?
Yeah.
Okay. So the first file says,
first line is saying that
what is the J stand for?
Yeah, J stands for job name. I mean,
Okay.
you can use any name if you like.
So the first line is for the job name. You can give it any name. CompBio MD. It doesn't matter, right? It's
and second one is the important one. It is saying that how many nodes you will be using for computing. I'm using 3 nodes here, but I think you should not use more than 1 for now. You can scale up to whatever you like, but be careful about using these nodes parameter because it can eats up a lot of computing resource. Okay. And for the next part is I'm saying that I will be using 12 minutes of my time. And yeah. Okay, so the most important part here is the sbatch account part. We have to write the project number here. Our project number is PGS0299. If you don't write it, you can't be able to run it in supercomputer. So yeah, that's the most important one.
So why don't you leave it? Let people copy and write it.
Yeah. Another thing is that I have included this command in the Slack hands-on file. So maybe you will need to download that file and open it.
কিন্তু রাত ওইটাই খুলে রাখো, ওইটা দেখুন, কারণ তুমি হ্যান্ডস-অন তো একই জিনিস দিচ্ছ।
হ্যাঁ,
তাহলে ওইটাই খুলে রাখো, বারবার
একটু আলাদা জিনিস দিচ্ছি ওখানে,
কিন্তু মানে এইটাই তো ইউজ করবে স্টেপ 4,
রাইট?
হ্যাঁ, তাহলে এটাই খুলে রাখো, ইটস ওকে।
Okay. So for the next part, module load part, you are just telling them to load the NAMD software. I don't know if you have gone through the, yeah.
ওদেরকে একটু সময় দাও, ওরা টাইপ করুক, পরে এক্সপ্লেইন।
Yeah, okay.
Oh, হ্যাঁ, আসতেছি। আসতেছি। তোমার কম্পিউটারে ওটা ইয়ে করতে হবে, আনপ্যাক করতে হবে, এটাকে মুছে দিতে হবে। হ্যাঁ, আবার আপলোড করা হচ্ছে আফটার এক্সটেনশন।
Any handful tutorial money?
Okay, so anything that starts with a hashtag after the sbatch command, they are just for comments. Okay, so if you have to type too much, you don't have to type the comments. Just go to the commands. Like that's, yeah. So you can type any comments. Okay, so because we are all distributing our course material through the Slack channel called course material, if you have not add that in your channels, just click add channel. It will give you the options, add the course materials, and then we have all the course materials so far there now, and we'll upload the future course materials there too. So add the course material Slack channel to your.
So, okay, let's get started once again. Yeah, so I think all of you have copied from the template submission file and paste your comments into your step 4 file, right? Okay, so these S-batch comments are for Slurm configuration, and you will see something like that. I think for you it will be, yeah, it will be similar, I think. Yeah, you will need actually you will need the need to change after run namd. You will have to use run namd command instead of namd2. Right, run namd replacing namd2. Can you do that? Good. And then you have to give the file path of step 4 equilibration.input file. It's a little bit tricky. As you can see, the term GUIs are in my home folder, and in that, oh, sorry. Huh? বাট তখন ওনাদের শেলে অ্যাক্সেস নিতে হবে। না সেটা আমি পারবো, কিন্তু ওনাদের তখন শেল। ওকে, opens an ON shell access. You'll see something like that. Um, oh. Hmm. তো হয় না পুরোটা আসলে। Okay, you have to detect the step for equilibration input. I think if you use ls command, you will get something like that. Okay.
Okay, so this step is to just, because these file directories name are really difficult.
Yeah.
So what you should do, open a shell, go to the folder where your step4.input file is there, right? So you can go cd/charm GUI /blah. So go to that folder, okay? And once you go to that folder, just hit pwd. If you remember from the Unix class, pwd is like present working directory. So it will give you the directory name. And in that input file that you are creating, change, copy that directory name to the in the input file. Okay, so go cd to your directory and just where the step4 is .sub is there, hit pwd.
Yeah.
And then instead of that, so you're going to change that to whatever directory. So,
Oh, this one is opened in the browser. Let me open it, another one. Oh, sorry. Yes. Just give the directory you have seen in your NAMD folder, charm GUI NAMD folder.
okay, so yeah, let's say it might be a confusion. So your folder name might be different than his, right? So make sure, so the whole idea is here you are saying, okay, you are saying run NAMD, and then you have to give the file that you want to run. So that file is under some directory, and name of the file is step4 equilibration.input. Okay, so now you all have the step4 equilibration.input, but your directory name might be different, slightly different, and that what you need to find out. So directory name is starting from
Home.
yes, so this is not home. hold on.
Yeah.
So-
Step 4 file is in home.
Huh?
Step 4 file is in home.
Okay, so,
So, yeah.
so this is, let's put dollars capital home slash at the beginning. Okay, to follow this, what it is saying is like, and you should follow these because right now the step 4.sub file is in your home directory, but it may not be in your home directory. It may be somewhere else and so on. If you did not put the $home in front, then it's going to look for a subdirectory. Whatever the step 4.sub is, it's going to look for a subdirectory under it and so on. And that may not be the case. It's better to give the full path name. So the first part, capital home, means whatever is your home directory. Okay, so it will be like slash user slash Rahat or slash user slash Shishir, whatever it is for you, that will be, sorry, yeah. So if you do echo, yeah, so that will be the first part. Under your home directory, you have a directory, whatever called charm GUI and so on. And then another directory, and then another directory. So what I want you to do is, like, instead of writing this huge thing, you can go to the directory where this file is. And
Yeah, let me show that to you. My charm GUI folder is in home. So ls
no, yeah.
charm GUI. I will go to the charm GUI 3 and then charm GUI 7 and then named. And then if I type pwd, it will give me the whole.
Let's do an ls to see, make
Yeah.
sure the file is there.
And also ls dev 4 equilibration.inp.
So if you just, even if you hit an ls, you'll see all the files there. And if this file exists here, then you want the directory where it exists. And if you hit the pwd, that gives you the directory name.
Yeah.
So you can copy the full directory, actually, then you don't even have to use the home. So you can copy the full directory. So copy. Oh, it's hard to copy.
Browser.
Oh.
I don't know if it's,
copied.
I'm not sure if it's copied. Let's see.
And then you can,
Oh, yeah.
yeah. So you can move, yeah, remove the whole directory name, not the file name. Yeah, and then hit the, yes. So now you gave the whole, you gave the absolute value of the directory. And then, you know, in the future, if you don't want to use the first three part, the users, PGS, and Shapayat Rahat, you can replace those first three part with dollar, yeah, dollar home.
Dollar home.
Okay, let's give them some time.
Yeah, yeah. Also, let's.
Okay, so anything that starts with a hashtag is a comment. You don't need to write those, copy those lines. Okay, don't worry about it. Anything that is without a hashtag, that's a command that's going to do the work. So the only line, command line so far we have is this 3 module load. That means we are installing the software. We are installing Intel compiler. We are installing software to run in parallels called MBA pitch, and we are installing the software called NAMD. So there are 3 command line, and then the 4th command we have. So all the in between, you don't need it. Okay. The 4th command line is run_NAMD, and then what files to run, you have to have the directory and the file. Okay. So those are the just.
There are some lines included is bcast or something like that. Best will be if you remove those lines. You don't need those lines because it comes from another template or another files. So yeah, just delete those files lines. Just open the template. these lines, you won't be needing these lines. Just these lines, you won't be needing these lines. Just delete those lines. Can you do that?
Okay, I'm going to go over, because this is getting a little complicated. I'm going to go over this file step by step and try to minimize it as possible. Okay. So first, let's go what are happening. The first line is just telling this file has to be interpreted by a bash, another command named bash. So that has to be, the shebang has to be there. The next line is called the next, anything that starts with S batch, they are for the slurm, and the options that we have is -j is the job name. You can give any job name. How many nodes do we need? We are going to run it on one node, because if you remember, each node has 28 CPU. That should be enough for this. The time, we're giving 12 minutes for now. It will be a short run. Exclusive, and all this has to be 2 dashes. Exclusive means like you don't want anybody else to run on your node. You just want your node to be run by yourself. Okay? So you are requesting a node just for yourself. And that's why it's called exclusive. Why do we need exclusive? I'll explain a little bit later. If you do not have exclusive, what do you do? Okay, and then the account is PhD. And then let's delete all these comments, because these are making confusion. So we're going to delete all these. Okay, so next part, our command is module load. So what is a module load? So module load, in your laptop, you can install any program that you want. But in a community resources, that's not possible, because different people can have softwares that will contradict with each other. So you always use module load so that you only load the softwares that you need. But how do you know which software is available? Okay, so if you go to your terminal, and if you type module avail, it will tell you all the softwares that's available there. Okay, so now exactly like we need the NAMD. Okay, so let's go to NAMD. Let's find NAMD. We are not there yet. Oh, was it before? Okay, NAMD is not there yet. Oh. We don't have NAMD there? Okay, so if you type module spider NAMD, it will give you the options of NAMD that's available. So you have two versions of NAMD, right? NAMD 2.12 and NAMD 2.13. So you have to choose between one of those options. Now here again, you have to go to the OSC website to see what other softwares you need along with the NAMD 2.3 or NAMD 2.12. Okay, so we definitely need NAMD. Let's say whatever Rahat was using is NAMD 2.13. Okay, so if we go back here, that's what Rahat is installing, module load NAMD 2.13. So we installed out of the hundreds of software that was available, we installed one of them, module load NAMD 2.13. Now, and if we try module spider, okay, so here is the other part. Now, if you type the specifically module spider NAMD 2.13, then it's telling you like you need two additional kind of software. One is Intel compiler, and there are different kinds of Intel compilers. So you need this combination of these and this. Okay. So one kind of Intel compiler, another kind of software that's called that's to run in parallel. That's the MVA pitch. That's for running in parallel. Okay. So those are the two other kinds of software you need. And you do the module spider your version, you get it. So I think Rahat chose one of the combination. I think he chose Intel 18.03 and MVA pitch. So that's where those informations are coming from. Okay. So you need, like I want to install NAMD. What other software do I need along with the NAMD? And that's where it's coming from. Now, the MVA pitch, I believe it's a parallelization. I haven't read it for a while. It's a parallelization within a core, but if you want to parallelize deep between nodes, like between two nodes, then you may have to get an MPI, another software called MPI, and so on. And if you do not put the exclusive option, then you are asking for, let's say, 28 cores, you are 28 CPUs. If you do not put the exclusive option, you can be allotted 14 in one, 10 in another, and 4 in another node. Okay, so your communication speed between the different CPUs is going to slow down, and you have to use a different kind, probably called MPI in that case. Okay, and that's why the exclusive option is good if you are happy with the 28 core within a node. I have 28 core within a node. So structurally, you can think a node means a box like your desktop. Okay, within the desktop, you have a motherboard. In the motherboard, you have the 28 CPUs. So they are talking to each other by direct silicon connections. Those are faster. Now you have two nodes being like two desktops. If you have two desktops, then you have to connect a cable between the two, and the communication is slower. Okay, and those communications go through a program called MPI. So that's the idea you remember. So if you are happy with a 28 core, you want it exclusive. If you want 56 core or something other than that, you should still say exclusive, but then you may have to, your communication will be a little slower, and you may have to use certain kind called MPI and so that's where all this cryptic message is coming from. Okay, so you have the module spider and so on. Okay, and then let's remove anything that we don't need. So I'm going to remove anything that I don't need. Okay, so it's actually a simple file, 4 lines of commands, 3 installation and 1 command. Okay, so the command actually says run MD. I'm going to run like something like we'll build the command. Run MD, that's the command. That's going to say run MD. And it's going to, now I have to give the input file. So some kind of input file. Okay. So what happens is, whatever this file will be saved, whatever this file, like whatever you are running on sub, step4.sub, whatever this file is saved, if you just say input file, so let's say it is saved under your home directory, and you say like, just run my input file. Yeah, whatever, let's say our input file is step4. So that's my input file. So it's going to look for that input file wherever this file is, but it's not necessarily there. So, and this is where the structuring of your data comes handy. You always want the files that are supposed to be together to be together. Like if I was running that, I would not have put the step4.sub in the home directory. I would have put it, I would copy it all the way to the directory to the NAMD, because this step4.sub file, it is submitting a NAMD file, which is in my NAMD directory. So that's where I would have put it. Okay. So you always put the file together where they should be. Okay. So this is right now, this is in your home directory, but ideally it should be in this directory. Okay. So, but now next is like, even if it is in this directory, you don't use just the file name. The reason is it's always a good practice to give the full directory name, because later in the, you ran it 6 months later, you came, it's just like, oh, I need to move this file in a different directory for a better organization. And then this will be an invalid command, because if you move that step4.sub to a different directory, then it's not going to find this file there, right? So it will be, so it's always good to give the exact full name, right? But again, we are lazy. We don't want to give the exact full name. And that's where we use a lot of alias. Okay. So one of the alias is $home. How do you find the value for the $home? So if you go, anytime there are lots of dollar values, you'll see is used in your script. Okay. And there should be a dollar on all capitals. So if you do echo $home, and it shows whenever you type echo $home, it's going to replace that with this value. Okay, so that's being a lazy and smart, right? Instead of typing all those big things, I'm going to type all the time $home, right? So your absolute path should be /user/this/username, but you can replace it by $home. So that's what it is, the $home here. So I'm going to be, $home and whatever file it is under. So that's the single line, and we are ready to run. I hope that clears all the confusion right now. And let's see, are we all ready to run? See, we have 15 minutes before we get hungry, so you have to run in 15 minutes. Yeah, so because we don't want to type a lot of things, either we personally or the people who are setting up supercomputer, they create what we call areas, that is like something specific power. So that will give you okay, so anytime you use dollar, so every instead of trying to write whole things that you have yeah. But why is that? Is it in the same file? I think it's a better practice to use the full record. Reason is like in the future you need to use the file here. But in the future, it might, if you just give the step4 implementation run now, but in the future, it will the file. No, future of good stuff. Yeah.
আমরা কি রান করতে রেডি? রাহাত দেখাও কি করে রান করবো। ও
আপনি ওই লাইনগুলো কেটে দিচ্ছেন? আচ্ছা, ওটা কিন্তু একটা দরকার ছিল, মানে ওটা So I think all of you have saved the file like this. Okay, so we'll now run the batch file for step 4 with the command as batch step 4 dot sub. So our job is now submitted. So if you type sinfo -u and then your username. Oh, sorry, SQ. Then you see that your job is now running. So you can see that in the ST or state section, it is written that it's in running or R state. If you see that it's in PD or pending state, then you will assume that it is the job is submitted, but OSC is just trying to submit your files in the compute node, and you have to wait for some time to run those files. Okay, so I think we have to wait for some time to run this.
Yeah. Why don't all of you run? Then we'll take a lunch break, and then we'll come back and look at the result. Yes. সব লাস্ট পোর্শন গুলো যদি ইয়ে থাকে ওটা সেভ করছে এই এক্সট্রা লাইন গুলো এটা কি খুলছে জাস্ট এডিট সেভ এখানটা কিভাবে খুলছে কোনোভাবে এইটা বন্ধ করে যে আমরা ইয়েতে টার্মিনাল space step এখানেই ছিল এই ডিরেক্টরি ছিল এইখানে না ওগুলো লাইন এটা কি একটাই কাজ করতে পারো মানে লাইন ব্রেক মানে হচ্ছে শেষে কোনো ঝামেলা হচ্ছে যেটা করে ভিআই ইনস্টেন্স আছে না ওগুলো ইয়ে না লাইন ওই প্রোগ্রামটাতে প্রবলেম আছে ভাবতেছি হ্যাঁ পুরোটাই করে কাজ করে instead of expect the units line words. ও এই যে এখানে ওটা আমি করলাম নাকি সব ভালো এখানে তো জিএসএম রাখতে পারো ওইটা ক্যাপিটাল জি Okay. That transfer. No, no, that's not. ওকে সবার প্রোগ্রাম রান করতেছে না কারোটা রান করতেছে না এখনো ও ওকে চল চল কেন রান করতেছে না হ্যাঁ Submit is that আচ্ছা এলএস ওকে হ্যাঁ ইসলাম ডট আউট আসছে তো তার মানে হচ্ছে যে প্রোগ্রামটাতে কোনো ভুল হয়েছে আচ্ছা তাহলে তার জন্য মানে কতক্ষণ আগে সাবমিট করছে হয়তো আমি জানি কতক্ষণ নাম হচ্ছে লেটস লুক এট বিআই ইসলাম ডট অথবা তুমি ওইটা থেকে দেখতে পারো ফাইল যে করতেছিল ওয়েবসাইটে গিয়ে হ্যাঁ ওখানে দেখো ইসলাম ডট আউট হ্যাঁ ওই যে ওইখান থেকে দেখতেছি ফাইলে দিতে হবে এখন নানোতে করো ওকে জানোতে ওই ফাইলটা দেখতে হবে হ্যাঁ ওই যে ইসলাম ডট সামথিং এখন থেকে দেখুন বিআই বা নানা হ্যাঁ এই তো ফাইল আছে নামটা থাকে দেখে এরা কিছু একটা প্রবলেম এরা রয়েছে Oh, okay. Okay, I see. Okay.
আমি এখানে এটা সেভ করেছি এটা সেভ হয়েছে বাট তারপরে এখানে যে রান দিব রান দেওয়ার পরে আসলে কিছু বুঝতেছিলাম না পরে আবার নতুন করে ওপেন করেছি এখানে রান দেওয়া লেখা
ওকে ঠিক আছে ওই ওটা কি রানের পারমিশন এরর রিড পারমিশন রাইট পারমিশন নাই হোম হ্যাঁ দেখো ওখানে রাইট ওর ইসলাম আউটপুট পাইলে দেখো পারমিশন নাই কেন ওর দেখি না ওটা নাম্বার না তুমি নাম সাবমিট করলে কি করে দেখি এটা একটা কি ইউজ করতেছো ভিআই বা নাম এটা কি ইউজ করতেছো এটা সেভ করলে তাই তো তারপরে টার্মিনালে যাও এটা না না এটা কিসে ঢুকছে এটা
এটা স্যার আমি এখানে ইয়া দিয়েছিলাম অ্যাটেন্ড করেছিলাম
ওকে ওকে নতুন তো আচ্ছা ঠিক আছে এটা এলএস দেখি এটা কোন এখানে কি আছে এখানে না এলএস মানে সাবমিশন ফাইলটা না ইটস ওকে ওইখানে যা ওখানে যাও এলএস আরেকবার হ্যাঁ ওকে তার মানে তোমার এখানে সাবমিশন ফাইলটা নাই তাই তো কোথায় সাবমিট করতে সিডিইউ চার্ম দুই করো সিডি চার্ম দিয়ে স্পেস দিলেই হবে স্পেস ট্যাপ করো ট্যাপ ইকুয়ালি ট্যাপ ট্যাপ এন্টার এলএস তোমার ওই স্টেপ 4.7টা করো তুমি কি এই নামে সেভ করছো স্টেপ 4.m নামে করছো ওকে এবার তুমি তো দাও s dash step 4.m s space step 4.m enter ওকে তোমার স্ক্রিপ্ট এমটি তোমার স্ক্রিপ্টে সেভ হয় না এটা কি নাম সেভ লিখতে হবে তুমি ক্লিক করো সেভ সেভ করতে পারেনি কোনো কারণে এই ফাইলটা খুলছে ভিআই হ্যাঁ তো ভিআই তুমি ওইটা তার জন্য ওই ফাইলটা এমটি হয়ে গেছে আবার লিখতে হবে ওই ফাইলটাতে সব ওভাররাইট হয়ে গেছে হ্যাঁ আরেক তুমি ওই পুরাটা দেখো কপি করে একটা ফাইল বিআই তে লিখবে না এখানে লিখবে হ্যাঁ নতুন করে পাবো কিন্তু ওকে হ্যাঁ আমরা লাঞ্চের পরে আইসা করতে পারবো হ্যাঁ হ্যাঁ লিখ করো লিখ করে ওই নতুন করে এই ফাইলটা আবার লেখো আর কি হ্যাঁ step 4.m টা বা step 4.m ডিলিট করে অন্য একটা ফাইল খুলে আবার ওইটা লিখতে পারো হ্যাঁ
আমার হচ্ছে এখানে একটা প্রবলেম দেখছিল যে আমার অ্যাকচুয়ালি কিছু 10 লাইন বেসিস
হ্যাঁ
আমি কনভার্ট করে ফেলছি স্যার আমার অ্যাকচুয়ালি আইডিয়া নেই যে এই লাইন বেসটা কোথেকে আসবে
যখন টেক্সট এডিটে এডিট করছিলাম মনে হচ্ছে ওরা যে টেক্সট এডিটের কোনো ক্যারেক্টার ওটা স্পেশাল ল্যাঙ্গুয়েজ বেটার যে ওগুলো ভিআই ইউজ করে না আমি সেটা আমিও পাইনি কিন্তু সামাও একটা প্রবলেম করতেছে আর কি হ্যাঁ এটা ভিআইটাই ইউজ করাটা বেটার কিন্তু ভিআই হচ্ছে যে প্র্যাকটিস করতে হবে
বলছে যে এক্সপেক্টেড ইউনিক্স
ও আচ্ছা ও আচ্ছা এটা ইউজ করতে ওকে গুড জানলাম এটা আমি জানতাম না ওকে ডস টু ইউনিক্স ওকে হ্যাঁ তারপরে কিন্তু এখন তোমার রান শেষ হয়ে গেছে ওকে হ্যাঁ আমার মনে হয় কোনো একটা আমরা এটা রিরান করবো লাঞ্চের পরে আমার মনে হচ্ছে যে কিছু প্রবলেম আছে আমাদের পারমিশনে দেখতে হবে হ্যাঁ সেটা এইটুকু করে Okay, I think we can take a lunch break because your run may not run because there are some permission issues, and maybe we need to look into that. Why the files are not running? Permission issues means like that NAMD program does not have permission to write in the directory. So okay, so that might be the problem. So why don't we take a lunch break, and we'll be back at 2:30. Okay. So it's a good lunch break. Enjoy. And we'll get back at 2:30. And oh yeah, we're already 10 minutes late. So okay, let's go for lunch. We're back at 2:30.
হ্যাঁ, এবং টাইমটাও না একটু বাড়াই দাও যদি। কারণ আমি 3টা নোট ইউজ করছি। অনেকের হয় অনেক